Good morning, everyone. Yeah, hello.
Good morning, sir.
Yeah. So there was
And
some
good morning.
confusion because I got some event cancelled. That is why it got delayed, I think.
Yes, sir.
Okay.
So good morning, everyone. Good morning, all participants. Welcome back to day 2 of this joint faculty development program on machine learning application in signal processing and communication engineering. We have with us our speaker from IIT Guwahati, Dr. Suresh Sundaram, sir. Today the session is on support vector machine. Suresh, sir, I'm making you the presenter now.
Yeah. Okay, thank you very much. So let us start. Okay. So what I will do is I'll just open my. Okay, so yesterday we covered about Bayesian decision learning. Okay, and then we talked about even support vector, this perceptron, right? Single layer perceptron. Okay, introduced the gradient descent algorithm and so on. Okay, so today's lecture is going to be on support vector machines. Okay, so the support vector machine actually became very popular in the 2000s. Okay, before the deep learning era. Okay, so there was a period where everybody used to use support vector machines for classification. Okay, so maybe probably somewhere in 2000 to 2010. Okay, so for that decade, okay, support vector machine was considered a very good classifier. Okay, with good generalization capabilities. Okay, so I would like to just talk about basic support vector machine. Okay, so it is used for machine learning, pattern recognition, regression estimation. Okay, and then the theoretical background behind a support vector machine is elegant, it is computationally efficient, and in large practical problems, okay, it is very effective. Okay, and then with regards to high dimensional feature space, it has a good simple mathematical geometric interpretation. Okay, especially when the data is non-linearly related to the input space. Okay, and we will talk about kernels. Okay, which will help you to keep the computations simple. Okay, so yesterday we discussed that discriminant function, okay, is a linear combination of the individual features, right? Individual components of X, right? Which is written as W transpose X plus W naught, W transpose being the weight vector, X being the input feature vector, and W naught is the bias. Okay. Now for a two-class problem, we said that G of X will be greater than 0 for positive class and less than equal to 0 for the negative class. Okay. So in particular, the function or the equation G of X is equal to 0, it is going to define the distance surface. Okay, that is going to separate the two classes. Okay, omega 1 from omega 2. And we say that when G of X is linear, okay, the decision is a linear the surface linear hyperplane. Okay, and we also mentioned yesterday that G of X has a geometric interpretation in the sense that it measures the distance of the feature vector X to the hyperplane. Okay, so as I was telling you, right? I mean, I'm just giving a review of yesterday's part of yesterday's lecture because it is going to be used today in the development of support vector machine. Okay, so that's the reason I'm just reviewing through. So you have this hyperplane which is there in 3D. Okay, and there is a point feature vector X. Okay, and you want to find out what is the distance of X, shortest distance of X to this hyperplane. Okay, and this is my decision surface. G of X is equal to 0. Okay, so all the samples in this side belong to one class, say omega 1. Okay, and all the samples belonging to omega 2 fall on this side of the hyperplane. Okay, so now the question is this value of Gx. Okay, if it's going to be positive, okay, it is going to lie on this side of the hyperplane, and if g of x is negative, it's going to lie on this side of the hyperplane. Okay, and if you also noticed that the highest value of g of x, okay, it can be shown that the highest value of g of x, okay, it means that the further the distance of x from the separating hyperplane, g of x is equal to 0. Okay, so in particular, the shortest distance of the feature vector x to the hyperplane, g of x is equal to 0, will be nothing but mod g of x divided by mod of w. Okay. All right. So now, okay, if you consider a two-class problem, okay, once again, you can see that the perceptron would learn this, would come up with a separating hyperplane, okay, that would help you to get the cost, okay, the cost that we discussed yesterday to 0. Okay, so you start from some orientation of weights, and then you keep updating using the gradient descent algorithm, okay, till you obtain an optimal set of weights that would help separate the classes, okay, right, with, you know, so with very good accuracy, that is with error equal to 0. Okay, so that would be the case where when you have a linearly separable data. Okay, so how does a perceptron work? We start with, you know, these are all different along different iterations. Okay, these are the hyperplanes, okay, that have been generated, and finally you will have a hyperplane, okay, say this hyperplane, right, which I'm showing here, okay, which will separate the classes from each other. Okay, all right, now we are going to talk about, okay, SVM. Okay, in talking about SVM, I would like to illustrate to you directly the example over here. Okay, so this is the hyperplane that a perceptron would learn typically, okay, where it will separate out the positive samples from the negative samples. Okay, now what does the support vector machine learn? Okay, so if you look at, this is a linearly separable problem. Okay, as you can see that the samples of class 2 are well separated from samples of class 1, and they're linearly separated. Okay, so what we do find here is that you know, you see here these two lines over here. Okay, these two hyperplanes which are going parallel to each other. Okay, so if you want to ensure the separability criterion between these two classes, you want to maximize this margin. Okay, so meaning you want to maximize this distance between these two hyperplanes. Okay, and obviously we will have to come up with some clever constraints, okay, in order to maximize this margin. So this is the philosophy of support vector machine. Okay, so you want to find out an optimal separating hyperplane that is going to maximize the margin, okay, between these two parallel hyperplanes. Okay, and so that's the main idea. Okay, now the question is, okay, how do you learn these two hyperplanes, and thereafter how do you get the separating hyperplane? Okay, so that's the main idea of support vector machine. Okay, so you can say that for all classes belonging to, all samples belonging to class 1, okay, you can definitely see that with respect to this hyperplane, okay, it is on this side. Okay, I'm just giving it in a very layman approach. We'll have to formalize it mathematically. And with regards to the samples of class 2, okay, with respect to this hyperplane, it is on this side. Okay, okay, is it clear? Okay, so now the idea is we want to find out, okay, how best can we separate the samples of these two classes by maximizing the margin between these two parallel hyperplanes. Okay, I will constrain my this one. I will constrain my analysis today, okay, only to the application of linearly separable data, okay? Because when you come to non-linear separable data, okay, which I will cover briefly, you will see that you will see that you will have some violations, okay? So you cannot actually have these two separating hyperplanes, okay, in this configuration, okay? So if you see here in these two separating hyperplanes, there is no training sample that falls in between them, okay, right? The reason is that the data is linearly separable, okay? So when your data is well trained and when the optimal weight parameters are learned, okay, the linearly separable hyperplane, okay, the maximum margin, okay, the between the hyperplane, okay, while computing the maximum margin in the hyperplane, we ensure that there are no samples, okay, that fall in this margin space, okay? But in a non-linear separable case, there is a possibility that you do have samples of the opposite class falling there because the data by nature is non-linearly separable. We'll come to that shortly, don't need to worry. So as long as you understand that the support vector machine has a concept of maximizing the margin between two separating hyperplanes, okay, and then that is the optimization criteria, and then subject to certain constraints which I will put forth, then we are done with the optimization problem as such. Okay. So coming back, okay, so we would assume that the data is linearly separable, so that W transpose Xi plus B is greater than 0 for all positive samples labeled as +1, and W transpose Xi plus B is less than 0 for all negative samples, which for convenience is labeled as -1. Okay. Now, since the training data is finite, okay, I would expect that W transpose Xi plus B is greater than or equal to epsilon, okay, for all positive samples, okay, and W transpose Xi plus B is less than or equal to -epsilon for all samples which are negative, okay? Because what I'm trying to say is there is a margin, right? So all samples of this class, okay, are less than some -epsilon. W transpose X plus B less than -epsilon, and then all samples of this class are greater than W transpose X plus B by greater than epsilon, where X is the training data. Okay. All right. Now you can combine. Okay. You can actually divide both sides by 1 by epsilon and write this as follows, right? Because scaling the discriminant function by a constant doesn't change the decision boundary. So I can write W transpose Xi plus B greater than or equal to 1 for all positive samples and less than or equal to -1 for negative samples. You can combine these two and write this as Yi times W transpose Xi plus B greater than or equal to 1 for all I. Okay, what is this I? I is the set of training samples, both positive and negative. Okay, so this is my constraints. Okay, so I have as many constraints as the number of training samples. Okay, so typically if I have n training samples, okay, training examples, then you will have n, okay, different constraints of this form. Okay, all right. So now, also very important to note is that for the linearly separable case, okay, there will be no training samples between the hyperplanes W transpose X plus B plus 1 and W transpose X plus B equal to -1. Okay, so what I'm trying to say is that there is no training samples here. Okay, there are no training samples in this band. So what is our goal now? Our goal is to maximize this band, okay, or this margin, okay, subject to these constraints, okay, that all samples get correctly classified, okay, right? Yi into W transpose Xi plus B greater than or equal to 1 for all I, okay. So now this turns out that this margin that I'm talking about, okay, this margin turns out to be 2 by mod W, okay, right? And I want to maximize 2 by mod W subject to the constraint that each of the training samples satisfy this relationship. Yi into W transpose Xi plus B greater than or equal to 1. Okay. So this is the optimization problem. Okay, you have a set of training examples. Then each of the training samples is d-dimensional. Okay, and I have two labels, +1 and -1, for positive and negative classes. Okay, and I want to ensure that my decision boundary classifies all the points correctly, which means yi into w toss xi plus b is greater than or equal to 1 for all I. Okay, and you have a constraint optimization problem of the form that minimizing half mod w squared subject to yi times w toss xi plus b greater than or equal to 1. So now I would like to talk to you about, okay, in the remaining part of the talk. Okay, so this is the optimization criterion of the SVM. Okay, so we need to actually learn the ways that minimize this constraint, minimize this optimization function subject to these constraints. Okay, and how many such constraints do you have? You have as many as L constraints, where L corresponds to the number of training examples. Okay, so now I would like to talk to you about how to solve a optimization problem of this type. Okay, a constraint optimization algorithm of this type. Okay, now most of you probably would have heard of Lagrangian multipliers, right? So which are typically used when you have equality constraints. Okay, so for example, you have, let's say, minimize f of x, okay, such that there is a constraint h of x is equal to 0. So then you would expect that the optimum value of x star, okay, that is going to minimize fx star is also going to satisfy this constraint h of x star is equal to 0. Okay, so now this is a very important concept. Okay, whenever your optimal value, okay, x star, okay, satisfies the constraint with equality sign, okay, then we say that that particular constraint is an active constraint. Okay, so let me just repeat it again. Okay, so I have a function which needs to be minimized such that h of x is equal to 0, and there is an optimal value to that function which is x star, okay, which is going to satisfy hx star is equal to 0. So whenever the constraint, okay, is satisfied with the equality sign, okay, at the point of optimality, then we say that the constraint is active. Okay, so let me talk about what are called inactive constraints now. So I have a function f of x which is minimized such that g of x is less than or equal to 0. Okay, so now if you take the optimal point x star, the point of optimality, that is going to minimize this function. Now there are two cases: either it satisfies the constraint with equality, or it does not satisfy the constraint with equality. So whenever the constraint is satisfied with the equality sign, you say that, okay, this constraint g of x star becomes active. Okay, and whenever x star satisfies g of x star less than 0, so which means that so there is a difference, right? So that means it is not satisfied with the equality constraint. Okay, then we say that the constraint, okay, becomes inactive. So this means to say that the minimum point, okay, x star, right, does not lie on the constraint. So what I'm trying to say is that if the optimal point that you obtain, right, lies on the constraint, then you say it is active. If it doesn't lie on the constraint, you say it is inactive. So coming back to this equation, okay, definitely when you are going to compute the optimization, we are going to solve this optimization criteria. Okay, we will see that there are a few of these constraints become active, a few of the constraints can become inactive depending on the value of w, okay, that you actually put there. Okay, so let me come up with some examples here. Okay, I want to minimize, say, x minus 3 squared plus y minus 4 squared, okay, over x comma y, such that x is less than or equal to 3, y is less than or equal to 4. So it is quite obvious that the minimum value that this function is going to take is going to be 0, right? All right, because if you put substitute x is equal to 3 and y equal to 4, you'll get 0 plus 0, which is 0. Okay, so the optimality point is going to be 3, 4, and you can note that this optimal point lies on the constraint x is equal to 3 and y equal to 4. Okay, so which means that since the optimal points lie on the constraint, they satisfy the constraint with equality sign. Okay, you say that they are active constraints. Okay, both the constraints are active. So coming to another example, same thing, same optimization, but the constraints are different over here. Okay, minimize x minus 3 whole square plus y minus 4 whole square such that x is equal to 3, y is less than equal to 5. You will see here that again the solution doesn't change, it is still 0. Okay, and so you put x is equal to 3 and y star equal to 4, right? The minimum value is still 0, but you see there's a difference here, right? This optimal point x star equal to 3 lies on this constraint x is equal to 3. Okay, and the optimal point y star equal to 4 does not lie on the line y equal to 5. Rather, it lies on y. It satisfies the constraint y less than 5. Okay, so that means to say that x is equal to 3 is active, y less than is equal to 5 is inactive. Okay, so coming back to our optimization problem. So we do have an optimization problem of minimizing a function subject to some inequality constraints. Okay, so see, whenever you have an inequality constraint of the form less than equal to, okay, some of the constraints will be active, some of the constraints will become inactive. Okay, depending upon the value of the optimal point. Okay, so the idea is, how do you mathematically formulate it? Okay, so what we do here is we compute what is called as the Lagrangian as the first step. So I will say f of x plus summation. Okay, there are say r constraints. Okay, so mu j aj transpose x minus bj. Okay, and mu j's are all the Lagrangian multipliers. Now I will ensure that the gradient of the Lagrangian with respect to x, okay, is equal to 0. Okay, and also I would expect that mu j star is greater than equal to 0. Okay, and mu j star aj transpose xj minus bj star, okay, is equal to 0. So what does the third condition say? So what we are trying to do is we are making some assumptions here that f is convex and continuously differentiable. Okay, and then we are also ensuring that under that consideration you have an x star which is a global solution. Okay, now why am I saying it's global? Because the function turns out to be a convex function. Okay, so that's the reason why it is a global solution. Okay, and yeah, so yes, so now at the optimal point x star, okay, it is going to be feasible only if it's going to satisfy these constraints. Okay, so these conditions rather. So that is the gradient of the Lagrangian is equal to 0. Okay, and then the mu I stars that you get, the Lagrangian multipliers are all positive and greater than equal to 0, and mu j star aj star x aj transpose x star minus bj is equal to 0. Okay, so now the question is, okay, what is the implication of the third statement? Okay, what is the implication of the third statement? Okay, okay, so what is the implication of the third statement? It means to say that if there is a active constraint, okay, so aj transpose x star okay, minus bj is equal to 0. So if that is going to be satisfied, okay, right? Okay, so mu j star, okay, can be 0, can be even a positive number. Okay, so that's what it is. On the other hand, if the constraint is inactive, okay, aj transpose x star minus bj is not equal to 0. Okay, so in which case mu j star is equal to 0. Okay, so I hope this is I hope it is clear. Okay, what I'm trying to say. So your mu stars that you get, they are always positive, right? Greater than or equal to 0. Okay, so when is the condition when mu I star is equal to 0? So that is the condition where aj transpose x star minus bj is not equal to 0. That is typically the case. Okay, so what we are trying to say is the following, right? Whenever you have an inactive constraint, okay, whenever you have an inactive constraint, then okay, the Lagrangian multiplier associated to it, okay, will be equal to 0. Okay, so this is known as the complementary slackness condition. So if you have understood till here, right? I mean, if you have understood to slide 22, okay, we are just formalizing that in the mathematical framework. That's all. Okay. Okay, so now we are quickly going to do how to do this optimization criterion. Okay, so I will write minimize half w transpose w yi into w transpose xi plus b greater than or equal to 1. You have L constraints. Okay, I will form the Lagrangian multipliers half w transpose w plus summation I equal to 1 to L mu I. Okay, then 1 minus yi into w transpose xi plus b. Okay, I'll write it in this form. Okay, and then you will have L Lagrangian multipliers. Okay, right? So, and then there's a vector that corresponds to that. Okay, so as you know, there are L constraints corresponding to the L training examples. Okay, so now I come back to these results and I just try to reformulate them as follows. I will take the gradient of the Lagrangian with respect to W, okay, and I will get this expression. Okay, you don't need to worry about this expression if you don't follow, but I'm just, at least the methodology should be clear. Okay, so that later on you can go back and read it up yourself. Okay, so I take the derivative of the Lagrangian with respect to W. Okay, I take the derivative of the Lagrangian with respect to B. Okay, and that is what I will get here. And then I need all the mu I stars to be greater than or equal to 0. And then this complementary slackness condition, which I was talking to you about, right? So mu I star into 1 minus yi x transpose w star plus b star is equal to 0 for all I. Okay, and this is nothing but the constraint. Okay, 1 minus yi into, so the same thing. Okay, I'm writing it as over here. So what we are trying to do is, okay, these are known as KKT conditions, so which means that at the optimal point, okay, when you get the solution x star, you would expect that it satisfies all these conditions, okay, which are known as the KKT conditions. Okay, so now let us look at the complementary slackness condition, because that is the most important one that we will have to look at to understand the idea of support vectors, right? So there are two possibilities here. One possibility is when the constraint is satisfied, okay, and the other two possibilities when the constraint is not satisfied. Okay, so let us take the case when the constraint is not satisfied. Okay, so which is an inactive constraint. It's not satisfied with the equality constraint. Okay, so it's an inactive constraint, so which means yi into xi transpose w star plus b star is greater than 1. Okay, so that means that constraint is inactive. Okay, it is not. So you have the optimal point w star b star, but you know it is not satisfied. It doesn't satisfy the constraint with the equality sign, so the constraint becomes inactive. So which means this guy is not equal to 0. So mu I star is equal to 0. Okay. Now other condition is, what happens if mu I star becomes greater than 0? Then you would require that 1 minus yi into xi transpose w star plus b star should be equal to 0, because this condition has to be satisfied. Okay, so this comes to a very important formulation. Okay, so if you look at the expression of the weight vector, okay, it is summation I equal to 1 to L mu I star yi xi. Okay, but from here you can make out that given the set of optimal weight vectors and the bias terms, okay, it is not necessary that all the constraints will be satisfied with the equality sign. So which means there can be some constraints which are inactive and some which are active. But what contributes to the generation of the weight vector are the set of active constraints. Okay, here are the set of active constraints where the constraint is satisfied with the equality sign and for which the mu I stars, okay, are greater than 0. Okay, so I will rewrite this as W star is equal to summation I belonging to S, which is a set of what are called support vectors. Okay, so what are support vectors? They are the set of feature vectors, okay, that have non-zero values of the Lagrangian multipliers, or those values of x for which the constraint is, whose corresponding constraints are active. Okay. Okay, so this is how you get the weight vector, and once you get the weight vector, you can compute the bias, because you know that yi times xi transpose w star plus b star is equal to 1. So you can pick up any I which is positive, okay, right? And then you can write down as b star is equal to yi, okay, minus xi transpose w star, because yi squared is equal to 1, right? If you recall, yi was labeled plus or minus 1. So if you take yi squared, it is 1. Okay, fine. So xi, so b star will be equal to yi minus xi transpose w star. You pick up any support vector, okay, and then evaluate and get the value of the bias. In general, we take all the support vectors, okay, and then compute as many biases, the number of support vectors, and then average them to a single value. Okay. Okay, now I've not talked about how to compute. So I've told you how to compute W, how to compute the bias. But the question is, how do you get this mu I stars? Okay, because yi and xi are known to us, right? Yi is the class label, xi is the feature vector. Okay, so how do you get this mu I stars? Okay, so it turns out that the mu I star is obtained by, okay, by formulating the problem in the duality mode. Okay, so I want to skip this because I think it can be too much heavy. So you compute the, you know, mu, okay, mu1, mu2, mu3, okay, so on, by coming up with a optimization, okay, so in the duality problem. Okay, fine. So I'm just going to skip these things, right, for your as long as you have understood so far, well and good. Okay, I mean, you just need to know that, you know, the support vector concept. Okay, what is the optimization criteria involved? What is this concept of maximum margin? How do you compute the maximum margin? How are the constraints generated? Okay, and some idea about active and inactive constraints. And the fact is that you will have some training examples for which the the constraint associated with it is active, so only those are considered, okay, in obtaining the weight vector. Okay, and to obtain the Lagrangian multipliers, we actually focus our attention to the dual problem, but that seems to be a little bit beyond the scope of this lecture given the time constraint. Okay, because we need to wind up in around 10-15 minutes, so that's the reason why I'm skipping these things. But I would like to tell you that the support vector machine training algorithm is quite intense. Okay, it's quite I don't say it's complicated, but you need to have a very strong background in optimization to understand. So I've just tried to give you a idea, okay, a brief idea of how Okay, the basic theory behind the training of the SVM. Okay, but the implementation of the training algorithm, you do have ready-made toolkits available to you. Okay, in MATLAB, Python, and so on. Okay, which you actually can use. Okay, which actually solve. Okay, using kind of very sophisticated algorithms of optimization. Okay, so now I would like to give a geometric interpretation to whatever I've covered so far. So, for example, you have two classes, say class 1 and class 2. Okay, class 2 is marked in this circles, and class 1 is marked as follows. Okay, and if you consider the separating hyperplane as this, so this is my margin, which gets maximized, and you see that it actually passes through some of the training samples, right? W times x plus b equal to +1 and W times x plus b equal to -1 passes through some of these samples, and whichever samples it passes through, you see that they are active, right? So the constraints will be active, so which means that this will have a non-zero Lagrangian multiplier. This will have a non-zero Lagrangian multiplier. This will have a non-zero Lagrangian multiplier. Okay, and whatever on other training examples, okay, they correspond to that constraint. Okay, their associated Lagrangian multiplier will be 0. Okay, because they are inactive. Okay, all right. So now let me talk about the non-linear separable case. Okay, I just want to give you some idea over here. Okay, I don't want to get into the mathematics because it's quite involved. Okay, so I'll just give in a nutshell the main idea. Okay, how you should approach this problem. Okay, so once again you have two classes, but you notice that the samples are non-linearly separable, so which means that you do have a guy from class 1 spilling into class 2, close to class 2, and a guy from class 2 coming towards class 1. Okay, so right now the question is that when building the hyperplane, okay, obviously the concept of maximizing margin still exists, but then you need to ensure that you also try to place the margin in such a way that the errors associated to the samples that fall away, right, like this sample and this sample, that these errors are also minimized. Okay, all right. So now for the samples that are correctly classified, okay, these errors will be 0, right, because there is no cost involved there. Okay, because they are correctly classified. Okay, so there is no violation as such. Okay, there is no deviation from the correct class, so the error will be 0. Okay, so these errors eta j's are nothing but proportional to the displacement or the violation. Okay, so this guy, this particular sample ought to have been here, right, at best over here, right, but then he has actually gone away, right? I mean, you understand, right? It is not fall, it has become non-linearly separable. Likewise, this particular sample ought to have been here at best, right? Or better to have been here. Okay, so what are we trying to say? We are trying to say that while you're maximizing the margin, take care of reducing these violations, okay? Reducing these errors, okay? So based on that, you can come up with the optimization criterion, something like this. Okay, so I'm going to maximize the margin or minimize half mod W whole square, plus at the same time minimize the violations, the n number of violations. So some of these violations can be 0, so they become 0 when they are correctly classified. Okay, and then there is a slight tweaking to the optimization criterion because you need to associate to these violations. So instead of 1, I will write 1 minus eta I. Okay, so like before, I compute the Lagrangian and then I compute all the KKT conditions over here. Okay, so I take the derivative with respect to W, with respect to B, with respect to eta. So eta is also now a parameter, but you need to optimize with. Okay, and then I will write down the constraint I require eta to be greater than 0, mu greater than 0, lambda is greater than 0, because you have two Lagrangian multipliers, right? Right, one set of mu i's and the other set of lambda i's. Okay, so two sets of Lagrangian multipliers, and then this is the complementary slackness condition, and then this is also another complementary slackness condition. Okay, so I'm not going to go through this analysis that much, but it can be shown that when mu I star is equal to 0, okay, right? So that is the case when the samples are correctly classified, yi into xi times with w star b is greater than 1. And when mu I star is equal to c, okay, it can be shown that yi into xi times with w star plus b is less than 1. So that means there is a misclassification. And when mu I star is between 0 to c, okay, okay, that is the condition where the constraint is satisfied, the constraint becomes active. Okay, so this can be proved actually through a systematic analysis by analyzing all these sets of equations. So I'm not going to do that because that could be a little bit more tedious for some of you. Okay, so you can take this from me that, you know, so when you have positive values of mu star, okay, they form the support vectors essentially. Okay, so that's the main idea. Okay, so you have two cases where mu star is between 0 to c and mu star is equal to c. Now, what is the c? C is the slackness variable. Okay, so c is a kind of a this one kind of a constant, okay, that is actually put there for penalization. Okay, okay, so now right, so what is the conclusion now? Okay, so the conclusion is that trailing vectors that lie on the hyperplane and the ones that get misclassified, they are taken as support vectors. Okay, so if you recall yesterday in the perceptual learning, while updating the weight vectors, we focused on misclassified samples, if you remember, and then we aggregated them, updated the weight vector for the next iteration. So in a similar way, here as well, okay, we consider training vectors that get misclassified at a given iteration and use them as support vectors along with training vectors that lie on the hyperplane. Okay, the pairs of hyperplane. Okay. So again, to get the mu stars, you do a optimization algorithm by considering the dual of the problem. Okay, so this is a small illustration. Okay, so you see all these samples are correctly classified, so their Lagrangian multipliers are 0. This sample falls on the hyperplane, so the corresponding Lagrangian multiplier is positive. These two samples, mu3 and mu4, they lie on the hyperplane, so they are positive. Mu1, mu2, okay, they are 0 because they do not lie on the hyperplane and they're correctly classified. But if you look at mu3, mu5, okay, so if you look at these two samples, right, so you will see that, you see that they are positive. Why? They become positive mainly because they have been, is a linearly separable problem, non-linearly separable problem, okay, and this guy ought to have been here and this guy should have been over here. Okay, so on kind of optimizing it, you see that actually you try to actually get Lagrangian multipliers that are positive, okay, and in fact, okay, equal to c. Okay, so that's what the c is equal to 5 in this case. Okay, all right. Okay, so I was explaining to you yesterday about what is called as a Covers theorem, right? So what is this Covers theorem? The Covers theorem is the fact that you can take any data which is in a lower dimension, map it to a high dimensional space. So for instance, okay, I can take data which is in 2D, map it to 3D, okay, and then I can actually get a separating hyperplane in 3D. Okay, so similarly here, we did this example yesterday. Okay, I have a 2D, okay, I project it in 3D, and then by a suitable mapping function in 3D, and then I separate the two data points, samples the two data points and classes, and then build the hyperplane. Okay, so we make use of this concept in dealing with the case of support vector machines for the non-linear separable class. So how we do that is by employing what are called as kernels. Okay, So whenever you run a support vector machine, it provides you with a set of kernel functions that you can exploit, okay, for efficient computation. And some of the kernels are polynomial kernels, linear, RBFs, okay, and so on. All right. So the idea is that, okay, let's say you want to do inner product of the form x transpose y whole squared. Okay. So x1, y1, y1, y2 whole squared. So I can write the same expression as x1 squared root 2 x1 x2 x2 squared inner product with y1 squared root 2 y1 y2 and y2 squared. So this means that, okay, you have actually generated, okay, this implicit functions, okay, in the high dimension, and then you're taking the inner product between them. Okay. But this is what is called as a kernel. So which means that the kernel does the same job, okay, implicitly, meaning that you don't need to know these mapping functions. Okay, you don't need to know these 5 functions that take you to a high dimensional space. Rather, you can actually use the kernel function available to you, okay, and implement the algorithm, okay, which actually does something similar to this. Okay. Now, x transpose y whole squared. Okay, this is a kernel, let us say. Okay, and what does this kernel do? It is as if that you map the data to 3-dimensional space by using a suitable function phi of x. Okay, and then you take the inner product over there. Okay, so so applying kernels, okay, make your job easier because you don't need to explicitly get to know these mapping functions. Okay, right? So let us consider another example, 1 plus x transpose y, okay, right, the whole square. So which will be 1 plus x1 y1 plus x2 y2 the whole square. Now this guy can be written as, has how many dimensions? So 6 dimensions, right? Okay. So it is as if that you consider 2 transformations which take you to 6th dimension. You take the inner product over there. Okay. All right. So, but then this kernel function, okay, makes you do the same operation in the 2-dimensional space itself. Okay, you really don't need to go to a high-dimensional space. So these kernel, this is what's called the kernel trick. Okay, so instead of figuring out which is the best transformation, okay, to the higher dimensional space, right, as dictated by the covers theorem, okay, the support vector machine comes up. In the training of support vector machine, you can use a set of kernel functions, okay, that you can use, okay, that would exactly do that mapping implicitly. Okay, so you really don't need to know the mapping, okay, but inner product can be computed by the kernel function in the space in which you are. Okay, all right. So any function cannot be a kernel function. So there are some conditions that need to be satisfied, known as the Mercer's condition. Okay. So some of the kernel functions that are typically used are polynomial kernel, radial basis function kernel, okay, sigmoid kernel, and so on. Okay. All right. So here are some examples of mappings. Okay. All right. So now these days, as you say that, when you have non-linearly separable data, okay, the support vector machine actually, when you run the support vector machine toolkit, you have a set of kernels. Okay, so those kernels actually do the job of implicit mapping to the high dimensional space and doing the operations over there for better separability. Okay, so I would encourage you that if you use the support vector machine toolkit for your application, please try to exploit the different kernels, okay, and try to run your algorithms and see, okay, the results that you get. Okay, all right. So now, so the support vector machine, okay, so it has some advantages. It has a good generalization property. Okay, of course, now it's not a really new concept. Probably it was around 5-6 years back. Okay, until deep learning networks took over. Okay, but still you can see that for many applications, right, it is used as a good classifier. Okay? Because you can actually build a support vector with limited training data. Okay. So compared to generative models, which require a lot of training data, okay, deep neural networks, which require a lot of training data for training. Okay. So if you have limited training data, provided your features are quite discriminative enough, right? Your support vector machine would do a quite good job, okay, in separation of the samples. Okay. And okay, so now I would like to just give you some applications of support vector machines. So handwriting recognition, 3D recognition, speaker identification, and so on. Okay. All right. So how do we do, before I wind up, right? How do we do? So support vector machine is a binary classifier. Okay. So how do we do support vector machine implementation for multiple categories? Okay. Obviously, what we covered yesterday, one versus one and one versus all. Okay. So I was talking to you about one versus one and one versus all paradigms, right? Okay. So you can use one of those approaches for implementing the SVM for multiple classes. Okay. I think with that, we can wind up. We have another 5 minutes before the next session, which I think is a discussion session itself. So any questions you can ask right now, or maybe you can ask once the session starts. So from my side, I'm done for the presentation. Yes, any doubts, please ask. Let me open the chat box. There are no questions so far.
Sir, there are no questions in the chat box till now.
Yeah. So I think the next session is going to start, right? I think the panelists, who are the panelists? All of them will turn up, or is it only selected for the next 11 o'clock?
Sir, it is not selected. Anyone can start the discussion, sir. From
Okay. So any questions, please ask.
Participants, if you have any queries, you can raise your hand or you can type your questions in the chat box.
You can ask any question related to machine learning. Okay. I mean, don't get constrained only to whatever I've taught. Okay. So feel free. Okay, so I think we can. So you want me to stay for the next session, or I mean, how is it? Or you'll give me a call when required. Hello.
Sir. Hello, sir. Sir, you can begin the session for the discussion also.
No, I don't know what to do. I mean, I've not been told anything, right? Should we wait for Ratnajit sir to come?
Yes, sir. We will
because
wait.
I'm not sure what I should do, right? Whether what
sir,
type of discussion, who's the chair? I think Agradeep is there, I suppose.
Arkadeep sir is also there.
Yeah, why don't you start?
Yes.
If you know what has to be done, actually.
For the hello, sir.
Hello.
Hello, Arkadeep sir. Yes, sir.
Yeah. Can you hear me?
Yes, sir. You are audible. Sir, am I audible
Hello?
to you?
Yeah. You are audible.
I'm
Okay.
audible. Okay, sir. You are also audible, sir.
Yeah. Okay. Suresh sir, actually, I think 11 we will have a open discussion. So participants will, I think they will ask any specific questions they have in mind, or any doubt in general if they have regarding the sessions. So that will be our next session actually for
Okay.
11 to 12.
Fine.
And thanks a lot for delivering this wonderful series of talks.
Thank you. Yeah. We have not met each other, unfortunately. So you should all come.
Yeah.
Not because, now it's like COVID, so I would not. But I'm in my office only, so you can drop in. You can take my number also. I'll post it and then we can.
Sure, sir. I'll call you.
Yeah. So
I'll call you and yeah,
I mean,
sure.
Konda Reddy also have not met. Yeah.
Sir. Sure, sir.
Yeah.
Dr. Suresh, this is Konda.
Yes. So we have not met. We have talked but not met, right?
Yes. Yeah.
Now COVID is also rising, so we are pretty.
Yeah.
It's good you joined before. I don't know what's going to happen.
Correct. Yeah, it's going to be really uncertain from now onwards. Yeah.
So I'll share you my numbers. Okay. It's there on the.
Yes.
Just check.
Yes, sir.
Sure, sir.
What your supervisor also has. So yeah. Okay, if participants are there, we can start the discussion, isn't it? Whoever has some questions.
Yes, I think we can start. It's almost 11 also time. Yeah, we can start.
The participants are there.
So Mr. Biplab, maybe we can start.
Yes, Arkadeep sir. You can start.
Okay. So we have a special session today. That's mostly we will entertain questions and answers and any specific or general doubts from the participants. Generally, the lectures mostly we talk about theories, and there are hands-on sessions also. But apart from that, we have kept this special session where participants can talk about their doubts, or some of the participants, they might be entering into this field. They are new to the field, and they might have many doubts regarding what kind of research problem they want to pick up, or how is it going to be in future. So in this session, we will have a open discussion about this. So participants feel free to unmute themselves and ask any specific doubt you have in mind. We have Professor Dr. Suresh Sundaram, Dr. Konda Reddy, Dr. Devango with us. We will try to answer, and you will also get enriched by taking your viewpoints. So you can ask any specific things, or general, whatever it is, you can feel free to ask these things in this session. Thank you.
Arkadeep sir.
Yes.
There is a query. Can SVM work well for big data?
Okay, since the last session was based on SVM, I think Dr. Suresh will be a better. I mean, he will
No,
be better.
anybody can answer, no issues, no problem. Yeah, so I think you can also go ahead. So I mean, these days deep learning is preferred. Okay, I mean, that's one thing. But what I would like to say is that when you have limited data, right? Like if you want to go through a generative approach, okay, then you probably have to compute the mean vector covariance. Okay, then you have problems of rank deficiency and things like that. So those things don't turn up actually in a support vector machine, because finally you're going to choose only a subset of your training samples or support vectors and then take a combination of them to get the weight. Okay, so obviously when you have big data, I mean, these days it is better to not look for handcrafted features. Okay, so you can go for deep learning architectures. Okay, is that doubt clear? And then you can put support vector as a backend, okay, like for better classification or for some ablation study or something. Okay, but when you have a lot of data available, better to, and you want to learn the features. Okay, I would suggest that given the current explosion of deep learning architectures, you should look for a deep learning method. Okay, is the doubt clear? I think, or anything you can add. Other members also can add, no problem. Agradeep or Konda Reddy or Debanga can add whatever I said. Hello, am I audible?
Hello.
Hello.
Yes, sir, you're audible.
Dr. Suresh, sir, yes, I can just add one thing.
Yeah, sure.
Traditionally, so basically, if you search for it, you will typically find out that the traditional machine learning algorithms, as your data increases, so actually deep learning algorithms can perform better as the data increases.
Yes, that's what I was saying.
Yeah. So as Dr. Suresh said, so this is exactly what you can look into. So you can see all the deep learning algorithms. They can really use the amount of data and increasing dimension and especially non-linearity of the data. So deep learning can actually transform from a very non-linear space to linear space. And then, in fact, deep learning you can use as a extracting feature, and then at the end, people also use SVM. So you can also kind of combine both of them in many cases. Yes, thank you.
Excuse me, sir.
Yes.
Yes, sir. So first I wanted to ask about soft margin SVM. The thing, the soft margin SVM would have three variables which we would need to be optimized. So in that case, do we have some function in MATLAB where we can solve for soft margin SVM also?
See, there are three parameters. No, one is this W, then other one is the bias, and I think there's this violation, that is that error, no, eta, what I was talking about. But you have these kernels actually that you can make use of. So you just run. I mean, I'm not very comfortable with MATLAB now. It's been a long time. So there is some SVM term, SVM predict, right? You can always search for some kernels. Okay. Right. So that is exactly what you should do, actually. I mean, that's an easier way, because the idea is it implicitly makes use of this covers theorem. It says that if a data is not separable in a lower space, okay, map it to a higher one, okay, to ensure better separability. Okay, so whenever you're dealing with a non-linear separable problem, it's better to look for kernels. And whichever toolbox you use, they have a set of kernels available to you.
Right.
Or rather, you yourself can develop your own kernel, okay, as long as you satisfy the conditions of the kernel, which is a Mercer's condition, right, which I just mentioned about, right? So you can actually come up with your self, generated kernel that you can use for, the mapping. Is it clear?
Yes, sir. So the thing is, sir, I am currently working in spatial smoothing plus SVM formulation. So what I've done is I have implemented the spatial smoothing using convolutional neural network. So that part is done. The thing is, sir, I was looking for an SVM formulation for spatial smoothing also. So the thing is, sir, I have formulated an SVM algorithm for that, a convex optimization function for that. The thing is, sir, to feed it to MATLAB, it is becoming a difficult task because the number of variables are more than 3 in that case. So I wanted to know whether we have another alternative method to feed my algorithm to MATLAB, because as I've seen, MATLAB only takes a quadratic programming QP problem as input to solve SVM and gives us weights and bias for that problem. So I wanted to know if there is an alternative method.
I mean, I'm not very sure. I mean, see, it also depends on whether you are. So I think you're doing some theoretical work, right? If I understand what you're saying,
Yes, sir.
you're doing some
Yes, sir.
theoretical work.
Yes,
Then you
sir.
have to check your theoretical formulation. Could be one thing.
Okay, sir.
So you may have to see it again whether your optimization is correct and whether your variables are okay. All right. So, I mean, your question has multiple answers, right? It could be some implementation issue which you are facing, or maybe a theoretical background that you have started with may be flawed a little bit, right? So, I mean, I think anybody else can. I think somebody has to be muted. Yeah, is it clear? Whoever asked the question.
Yes, sir. I got it.
Of course, these days there are a lot of versions of SVMs. Okay, so there are a lot of versions. There's a 1+ SVM. There is something some new SVM, and things like that. So you have multiple versions of SVM. Okay, all of them actually rely on the basic idea of whatever I discussed today of KKT, applying KKT conditions. Only the optimization criterion changes with the constraint. You should ask people to mute. I think only except the speaker.
Mr. Biplab, maybe there are many noises.
ఇది ఇప్పుడు మా దగ్గర ఉన్న ఇది
Hello, Mr. Biplab.
ఇవన్నీ ఉన్నాయి కదా వీటిని కూడా దీని మీద ప్లేస్ డెమాన్స్ట్రేషన్ కోసం మీరు ప్లాన్ చేయొచ్చు వాడప్పుడు ఎడ్యుకేషనల్ హార్డ్వేర్ బాగా
Hello, participants. Can you please mute yourself because it is too much noise here. Can you please mute yourselves, and if anyone specific has a question, unmute and then ask. Can you please mute everyone?
సార్ లీనియర్ మోషన్ ఇప్పుడు మేము ఒకటి 3.5 పిల్లలు చేయగలగడానికి పిల్లలు అంటే ఒక ల్యాబ్ చేయించడానికి కష్టం క్లాసు ఏమన్నా చేసుకుని రీసెర్చ్ కోసం అయితే ఓకే ఫైన్ చేయాలంటే పిల్లలు చాలా షార్ప్ గా ఫాస్ట్ గా చేయగలిగారు అందుకని మేము ఓన్లీ కొంతమంది స్పెసిఫిక్ స్టూడెంట్స్ కి ట్రైనింగ్ ఇస్తాం ఆ లెవెల్ తీసుకెళ్ళి మనం
Participants,
చేయగలిగితే
please mute yourselves.
ప్రోగ్రామింగ్
Hello.
వెరీ డిఫికల్ట్
places.
గైరోస్కోప్ యాక్సిలరోమీటర్ అన్ని ఇంటర్ఫేస్ చేస్తాం
Mute everyone.
ஈசி டிபார்ட்மெண்ட் எல்லாருக்கும் சொல்லியிருந்தோம். ஏன்னா அவங்க வந்து
If you have any specific questions, you can post in the Q&A or the chat section.
Can we ask?
Sure, please go ahead, please.
Okay, sir. Sir, yesterday for neural network, I have some question. When we are using any data, you are taking the features for classification using neural network. But if we will not use any feature and we'll only take only signals like modulated signals, PPSK, QPSK, like this, then we will use the modulated bits, yes, for the input. My question is, what is the input for the neural network for a signal?
So it's not very clear. Please correct me if I understood it wrong. So you're asking what is the general practice of feeding the neural networks? What sort of features are sent? Is it right?
Yes, if we'll not take any feature, only we'll take signal. Like BPSK modulated signal, QPSK or QAM.
So you're asking, can we send it, or is it the best practice to send those modulated signals, right?
Yes, the input of the neural network is the what?
Okay. So generally, if you use shallow neural networks, which are limited by the capacity, it's a better idea to extract the suitable features and feed the neural network. For example, if you have the domain expertise, you can come up with effective features. So that requires domain expertise. You need to understand what we are doing and what features would help us do the task. If you are not very sure, you can work out with deep neural networks, which have very enlarged capacity and which do they do the task for you of feature extraction. Then you can just provide the signal. You don't need to worry about feature extraction. Automatically, the task drives to find out the suitable features. Okay, this requires a lot of data. Unless you have a lot of data, this doesn't work. May not work, I would say. Yeah, so the short answer is basically if you have small data, you have to find out the suitable features for the task. But if you have a lot of data, go for very deep neural network and provide all the data. Based on the task, the features will automatically be found by the neural network. So one of them requires domain knowledge. The other one may not require so much of domain knowledge. Feature extraction in any task requires domain knowledge. You need to understand the signal, understand the task, and need to find out or even come up with novel features to solve the task. So earlier, pre-deep neural network, pre-deep learning, machine learning was all about coming up with features and then use a off-the-shelf classifier like SVM, neural network, and any decision trees, some things like that. There was a distance separation between the feature extraction and the classifier part. But when the deep learning happened and a lot of data is there, you don't need to really work on the feature engineering part. Just provide the signals as is and make sure the deep neural network has enough capacity and drive with a suitable objective, and features will automatically be learned. Right. Am I clear?
Yes, sir. Sir, if we will not use the deep neural network, the multi-layer neural networks, CNN, we will use simple flat functional link artificial neural network, single layer artificial neural network. At that time also, we need to classify their features?
Yes, if you are using smaller neural network for any reason, you have to come up with better feature engineering, need to come up with intelligent features, effective features. Yeah, that part we have to do. Yes. Yeah, so I'm not able to suggest you what sort of features for the signals you mentioned. That requires domain knowledge. Yeah, so you need to understand the signal.
Dr. Reddy.
Yes, sir. Please, sir.
Yeah, so I may add to these things. For example, she mentioned about, say, BPSK signal.
Yes.
So phase modulated signal, essentially their envelope is constant. So
Yes.
what will change? Phase or frequency modulated signal. Their signal envelope is constant. And what changes is the phase. For example, in a BPSK, the phase will be, if it is a simple BPSK, it will be 0 or 180 degree. So the change in phase, now this signal will be in the presence of noise. Now, when you add noise to the signal, and if it is additive noise, then the amplitude also will change. But we have the technique of using, say, sending the signal through a limiter to remove the amplitude variation. So maybe the example she is giving here, the primary information that need to be sent into the neural network is the phase information. So this is the way the understanding of the signal itself goes into extraction of feature. Does it make any sense?
Yes.
Okay. Okay, sir.
Dear participants, you are requested to raise your hand.
We have modulated. Then that bits are in terms of +1 and -1.
Yeah, +1 and -1, what it refers? It refers phases. +1 is 0, no phase change. -1 is 180 degree phase change.
Phase shift.
Yeah, yes. So this is the distinct feature by which you can recognize.
Okay.
When
When
you
we
consider QPSK, you will have 4 phase levels.
Yes.
But if you take a QEM signal, there the amplitude as well as phase will change.
Both are changing.
Yeah. So that's why extracting those information, which information will be useful in training your model, that is very, very important.
Yes, sir. If we are estimating a channel and we are directly simply giving it squam signal of this at that time, so we'll have to extract that feature of phase and amplitude.
We have another participant, Mr. Harshavardhan Ahire. You are unmuted. You can raise your query.
Thank you, sir. This is Harshavardhan. I'm pursuing PhD at VJPI and I'm working in the area of error correcting codes. Sir, I'm trying to use machine learning as a decoder for low density parity of codes. I have successfully implemented the decoder using artificial neural network AN and with the shallow network. And I'm trying to implement this by making use of support vector machine. But the ambiguity for that is since the noise factor which we are using, it's a random variable. So there will be a chance for a symbol. Some symbols, the value for the feature space, the value for 0 will be some value, and that same value will be represented for some other symbol as 1. So if that scenario comes, can we use support vector machine? And if we can use, then how this scenario can be overcome?
So this is binary, yeah, you're talking about?
Yes, sir, binary only.
Then
we are
there is
converting
something.
everything into symbols.
Yeah. So there is something called as naive-based classifier, actually, which is suppose the basic one. Okay. So you can just go through that and see, actually.
Okay. Can you please repeat the name, sir?
Naive base, NAIVE base. So base, BAYES. I'm just giving an idea, okay? I'm not saying so you can look at that and then see how they extend it to, if there's some work extending to support vector machine. I'm not aware of it, but you can just see, actually, because you're talking about bits, no? You're talking about bits toggling, right?
I'm interrupting you. When we receive the values from the channel, at that moment they are in the form of some random values, and then it is converted into a log likelihood ratio, that is LLR values, and then those LLR values are sometimes represents the zeros also, and sometimes it represents one also because of the channel randomness of the channel.
So
that will be a problem.
Okay. So what is your input? Your input is a continuous floating value number, or is it binary? Because if it is binary, then you have to go for some naive based kind of thing. So that is what I'm asking you.
It's a log LLR values. That is nothing or not the binary value. It's some value between 0 to 1, or 1 is represented by negative values and 0 is represented by positive values. Between 0, +1 and -1.
No, that's what I was telling. So if you have the log likelihood ratio, you can find out the threshold and then decide on the decision, isn't it? Like what we discussed yesterday. That is also a simple way to do. So why do you want to go to a support vector machine?
The threshold can be used, but the thing is that because of the randomness, sometimes 0 may be represented as a negative value because of the noise added noise to the symbol.
No, so what is your question? I'm not clear.
Because of this problem, that is in support vector machine we separate the classes by hyperplane. There may be a chance that a class, a symbol which is representing 0, that may fall into the class of 1. This can be used, this support vector machine, because there are many cases where we are transferring 1000 block size of 1000 bits. And then in that 1000 bits, sometimes it will be, because of the noise, 0 might be represented as 1 and 1 might be represented as 0. Then can we use support vector machine and
So
can we overcome it?
No, that's what I'm telling you. See, if you have a ground truth, okay, right, and then say the processing, there's a misclassification happening, then you can recover. Okay. But let us say at the initial, because I'm not in your area, so I mean, Professor Rathindra sir can come.
So let me, Dr. Sundaram, let me put his question in proper perspective. A channel coding means we take a string and add redundant bit to it.
Okay.
Which will actually try to resist the impairment produced by the channel. And in the decoding, these redundant bits are removed. The coding is done for error detection as well as for error correction. Error correcting codes are difficult and very, very robust. So what type of coding scheme you are using? Which coding scheme you have used? Encoder, decoder is?
I'm working in low-density parity check codes. I'm using quasi-cyclic LDPC for the encoding.
LDPC. You are using low-density parity check code, huh?
Yes, sir. Yes, sir.
Yeah. So that part, maybe we will invite another expert. Devanga.
Yes, sir.
Can you get him connected to Kuntal?
Yes, definitely, sir.
Because this is his area of work.
Right. So please send. Please put your name and email ID in the Q&A box. Then I will able to connect you to Dr. Kuntal Deka. So he's an expert in this area, so he can help you definitely.
Thank you very much, sir.
Yes. Thank you.
Surely I'll send you a private message into the chat.
Yes.
Sir, next participant is Sinayan. Sinayan, you are unmuted. You can raise your query.
Am I audible? Hello?
Yes, ma'am, you are audible.
Okay, thank you. My query is actually I am working on IoT. My research area is IoT, and I am concentrating on energy efficient communication in IoT. So, may I know the relevance of machine learning in energy efficient communication in IoT? The application of machine learning in energy efficient communication in IoT.
Can I respond to this?
Yes, sir.
Can I respond to this?
Yes, sir.
Yeah. So I will not go into very detail.
Okay.
The IoT devices, these are operated with batteries, and they are designed to operate for a long life. So how it is achieved? It is done by appropriately designing the sleep and wake up cycle. Okay.
What
So
is that?
when the
I
device
didn't
is
get.
to go to sleep and when it is to wake up. So in that way, the energy saving is made. And in recent times, people have applied lot of techniques, AI-based techniques, to actually optimize this sleep and wake up cycle for the IoT devices. You please leave your email ID and name and email ID with our E&ICT people. I'll send some of the recent references that has been that have addressed this issue.
Okay, sir. Thank you so much. Where I put my mail and mail ID and name?
You
In
put
chat
it in the
box?
chat box. You put it in the chat box, and then we'll
Okay,
get
sir.
back to you. Okay.
Sir, these sensors, IoT devices are battery operated and low power devices. So
Yes.
suppose we perform some
So
computations.
most of these devices actually are not operated in a continuous manner.
Yeah,
So
sir.
it transmits only intermittently, and most of the time it remains in the sleep mode. So many a times this transmission is event driven. That means you need to change senses the changes in the environment, and then it transmits the data. So it is the optimization of the sleep and wake up cycle is very, very important for extending their lifetime, and many works have been done towards that direction. So I will share you with some latest references. So please leave your email ID in the chat box, name and email ID. We'll get back to you. Okay.
Sir, in the papers, they mention about the machine learning techniques for energy efficient communication.
Yes.
Okay, sir. Thank you.
Thank you.
Sir, there is a query from the participant side. Can you suggest some ML application in the design of data converters, ADC or DAC, used beyond 5G communication?
Right now, I cannot respond to it. Maybe our signal processing people. Devangu, can you respond to it right now?
Can you repeat the question again? Let's see if I can address it. Yeah.
Sir, the question is, can you suggest some ML application in the design of data converters, ADC or DAC, used beyond 5G communication?
Right. So since it's on 5G and related things, maybe Arkadeep can actually in a position to answer this question.
Okay, so intuitively, what I feel is probably ADC in DSC. If you go back to the basics, it deals with some quantization and quantization noise. So, so while designing ADC and DSC, probably quantization may serve as a quantization noise may serve as an important optimization criteria. So obviously using machine learning, what you can do probably is DSC may not work well for every scenarios because the network is very heterogeneous, right? So network is heterogeneous, the traffic is also varying with time, channel conditions are also varying with time. And if you go towards beyond 5G, then the heterogeneity will be more, because if you apply this, if you are working in a millimeter wave scenario, then the traffic conditions will also change very rapidly. And because of different type of applications that are being used nowadays, traffic conditions might change very rapidly. So so basically depending on the environment, that a particular type of DAC or ADC might not work well. So in this scenario, machine learning might help because it might make it adaptive. So if you employ some kind of machine learning algorithm at the transmitter or receiver side, which maybe in a semi uh, in a after a large time, after a large time, it will automatically adjust the parameters, the hyperparameters associated with DAC or ADC based on the signal amplitude also. So for example, if there is a if the amplitude variation of the signal is too much, then one type of ADC might be better. If the amplitude variation is small, then another type of ADC might be better. So using machine learning, this can be done. So we have to put this in a appropriate optimization framework. And then if you if you remove the assumptions that all these parameters of the network are not known, which typically happen in today's network, and then you can use machine learning to learn this parameter on the fly. So to put it in simpler words, so suppose the traffic condition or the channel condition, these are varying, or the amplitude of the signal you are dealing with, that is also varying, then you do not have the knowledge of the parameters driving this driving these things. Then you can use a machine learning algorithm which can automatically learn based on the type of signals that you are dealing with, and make your DAC or ADC an adaptive one. Uh, does that answer your question?
Dr. Orgo, I would like to add one or two points to this.
Sure, sir.
So the typically, for example, the very high speed ADCs used today and high resolution, say 20 gigasample per second, or having resolution 8 to 12 bit, the typical power consumption is of the order of 500 milliwatt. And now if you consider, suppose, a massive MIMO system with each RF chain connected with ADC and DAC, the ADC DAC power dissipation itself become very, very huge. And this is a big problem in the design of such systems. I thank you for raising this issue, ADC, DAC, because this is a very challenging problem for the industry. Now, two approaches are usually adopted in practical system. One is going for high resolution, low speed ADCs in parallel. So this is one solution people try. And this has the disadvantage of error flow and system performance. Because of the mismatch of the ADCs, it creates a problem. Another direction in which people tried is high speed but low resolution. You limit the resolution bit to 2 to 3 bits, go for very high speed. Then the burden is now transferred to signal processing algorithm. And definitely, given these options available, machine learning can play an important role in optimized design of ADC systems. This is a gray area and many research activities are going on.
Thank you, sir. So now we are unmuting Dr. J. Rangarajan, sir. J. Rangarajan, sir, you can raise your query. Sir, you are not clearly audible. Sir, you are unmuted. You can raise your query. Sir, your voice is not clear. Rangarajan, sir, you are not audible clearly. You can raise your query in the chat box also.
Yes, sir. Sir, I will send in the chat box.
Rangarajan, sir, I think you are audible now.
Yes, sir. Yes.
Sir, you can ask your question. Sir, since you are not audible, you can type your question in the chat box. So, sir, we are giving the next opportunity to Mr. Prem Kumar. Mr. Prem Kumar, you can unmute yourself and ask your question.
Good morning, sir. Sir, may I audible?
Good morning, Prem Kumar. You are audible.
Sir, in signal processing concept, the machine learning can be used in orthogonal techniques. Whether any possible to implement in OFDM concept, which is related to orthogonal techniques. Sir, may I audible?
Yes, Mr. Prem Kumar, you are audible.
I post my queries in the chat box, sir.
What is your query? It is not understood. OFDM is a multi-carrier system, is not it?
Yes, sir. Yes, sir. In signal processing and machine learning can be used as a orthogonal techniques, which is related to any concept in OFDM techniques, sir. Any possible to
That's
implement?
what we are trying to understand your question. OFDM is a signal transmission technique.
Yes,
and
sir.
this is used in 4G LTE system.
Yes, sir.
So what is the basic idea in OFDM is that you take a stream, high-speed data stream, divide it into low-speed substreams, and send it via orthogonal carriers. And this actually reduces this effect of Doppler and other things. And this type of multi-carrier modulation has become the standard. And next advancement of OFDM is, of course, OFDM-A, the multiplexing, where you can actually add drop carriers. But there are certain issues also. Peak to average power ratio is an important parameter in OFDM. So this is a concept which is developed for combating the channels to improve the mobility and the data rate. So in signal processing, what is your question? How you can utilize these concepts, or what is this? What is the question? Can you pose it a little bit more clearly?
Sir, orthogonal techniques, sir. In signal processing, machine learning can be used as a orthogonal techniques. How it is possible?
Orthogonal technique means what? Orthogonal.
That is OFDM, orthogonal frequency division multiplexing.
So I am not very much aware. The other panelists, if they would like to respond.
Okay, so thank you.
So I'd like to say something regarding this. Probably if you are asking this, that whether machine learning can be useful in WebDM based systems, then yes, definitely, because 4G, as Professor Ratnajit pointed out, 4G uses WebDM, 4G LTE system uses WebDM, and there has been many studies based on machine learning applications for this LTE kind of systems. And for example, this resource allocation is one of the area where you allocate channels. So the channels that has been used as in a subcarrier for the WebDM, that time frequency, how these channels can be allocated, and based on the user arrival pattern, channel conditions, in an adaptive manner, those things has been already captured in the literature. So if you can send your mail, I will forward some literature on this to you. How machine learning, all these techniques like supervised, unsupervised reinforcement learning, all these kind of techniques has been used in these issues related to WebDM systems.
I also want to add one. I also want to add one thing, sir. The OFDM basically the 4G LTE technique. So we require the input data and the output data, the label data. So many applications from antenna selection to channel selection, sub-carrier channel selection. So we basically require in offline the data, the received signal at the base station, and the label delta will be the transmitted signal from the station node. Thus, we need two training data, and in online we just use machine learning, any machine learning techniques. So these are the application from antenna selection to channel selection.
Sir, the next query is from
will come under the broad umbrella of resource allocation. Thank you. Please go ahead.
Thank you, sir. The next query is from Dr. Rangarajan, sir. If the technology is going on, to what extent it is possible to make optimization?
Can you please repeat the question?
Yes, sir. If the technology is going on, to what extent it is possible to make optimization?
Yeah. So as I mentioned in that introductory talk, the traditional system design methods, we use mathematical modeling. We start with a mathematical model. For example, if you take a communication system, so you have a source, you have a channel. This channel may add noise, it may add interference, and then you have a detector, and you have detection techniques which have been developed. So the traditional method, we go for optimization, apply optimization algorithms based on the mathematical model of the system we develop. Now, conventional optimization techniques, they can improve the system performance provided your mathematical model also captures the characteristics of the system very appropriately. Many a time, we build statistical we build the model based on the statistical distributions. For example, when we are modeling the effect of noise, we are considering a Gaussian. When you are considering effect of fading, you are using, depending upon whether there is a multipath, direct path, or it is non-line of sight, Rayleigh distribution. So ultimately, we are trying to visualize our system as a mathematical model, and then on top of this, we apply our optimization tools to improve the system performance. And before deployment, we can have some idea how the system is going to perform in practice. But as I mentioned again, that it is very difficult to build those mathematical models in a very robust way, taking into account every interaction. So here possibly the AI and ML will play a major role because they can learn from the environment. The system becomes smart and keep learning from the environment, and that learning is applied in improving or optimizing the system performance. So you are actually giving inbuilt learning capabilities. You are not just following certain set of rules. It's not a just rule-based system or threshold-based systems. You are trying to implement more and more flexibilities in the system and taking into account, but it requires the system to learn it as human being takes time to learn from the experiences. So these algorithms also, they will learn. Maybe the first attempt, second attempt, they will not be able to that accurate, but when their learning is sufficient, they will be able to optimize the system performance more perfectly. So it's a continuously evolving process. What Dr. Ranjarajan has tried to tell, I try to answer this in this philosophical level. Of course, the implementation to exact system will vary. I invite my other colleagues to please share their views on this.
Sir, can I add one point to this?
Yes, yes.
Yeah. As described by Professor Bhattacharya, so this is actually I will just explain this whatever he said to an example. For example, take a system where there is a 4G base station and a Wi-Fi access point. Okay, and there are users that are arriving. So now, if I know the arrival rate, often in the telecommunication sector, we model the arrival as a Poisson process. So if we know the parameters of the Poisson process, then we can offline we can make some algorithms, and then we can. I mean, machine learning is required for that. Now, for machine learning, if we do not know the arrival rate, because knowing the arrival rate of the users is very difficult and time also. So if we do not know the arrival rate, then if we employ some algorithms like Q learning is one of the basic reinforcement learning algorithm. So what will happen is that it will learn. So it will take some time to learn. After, say, for example, you run the algorithm for some iterations. So whenever there is an user arrival, you make some changes to your parameters, and then gradually it will learn. So maybe after say 100 or 200 or 300 arrivals, you will see that the performance is hitting the optimal one. So there are mathematical proofs also that this kind of algorithms actually converges to the optimal policy in the long run asymptotically. So therefore, there is no loss in the performance if you look at it in a t tends to infinity kind of perspective. But if you look at finite time also, in finite time there might be loss because it is learning from the environment. But how much loss will be there in finite time, that guarantees are also provided in current literature. But if you run it for a very long time, definitely it will converge to the optimal solution. So in that way, there is no loss in the performance if you view it in a longer time scale. Thank you.
Thank you, sir. Sir, there is a query. In developing hearing aid for elderly people, can you suggest the type of machine learning algorithm to be applied?
So I can add something to this question. I'll try. So any kind of whenever you are trying to use a machine learning model, so the most important thing is to really clarify what is the input and what is the output. But even before that, you have to clarify what is your goal. So what is your problem, right? For example, are you trying to reduce the noise? Are you want to make more, want to capture directional hearing? And or maybe the system can automatically find out, who is speaking, and then maybe do some kind of smart way, reduce some unwanted voices. So that thing I think should be clear it's not clear in the question, but anyway, so depending on that. So for example, there are a lot of algorithms that might be used for removal of noise from speech. So that's one example. And also maybe, see, I'm not an expert in speech, but maybe there are some algorithms that can automatically find out some directionality from the speech it is capturing. So I think first you have to define, if you can define what is your input and what is your output that you are looking for, then I think it will be easier to answer this question.
Also in echo cancellation, there is some non-linear signal.
Right.
So we can model that using a neural network.
So is this a temporal sequence, right? So
Yeah,
have you tried some algorithms in your project? Can you give an example that have you even tried, or are you just thinking of applying it?
I am thinking, sir.
You're thinking. So for example, you can look into, for example, most probably if you are looking for supervised algorithms, you need some data set where you find out, some data set with a label data, right? So you have the input data, input samples, and then corresponding labels, right? Like for example, maybe you have a data sample where there's echo, and there's one sample which is then you find out what is the sample without echo, right? Echo. So in that case, you can find out first. You have to find out whether you are using a temporal. You have a temporal sequence, or you just have a particular, one static sample. So it's just a classifying, or actually you are doing some kind of processing a long time. So then, for example, if it's a temporal sequence, you can go for models like LSTM or transformers. So those are the models that you can check. And if it is just classifying thing, then maybe you can also check the standard feature extraction CNNs, where you not say CNN necessarily, any kind of deep neural network you can search for that can extract some useful features from it, and then use that features for classifying using some kind of linear classifier. So these two things, I think, kind of models that that you can look for. Yeah, other panel members can add also if they have any input in this. Thank you.
Okay, Lakshmi Choudhury. Okay,
Sir, the next participant is Lakshmi Sogule. Lakshmi ma'am, you can unmute yourself and raise your query.
Hello, sir. Good morning to all. Sir, I have a question. In audio processing, if I'm doing feature extraction, is there any Python library which can calculate mean dominant frequency or dominant frequency, maximum and minimum dominant frequency, and mean fundamental frequency, and all that stuff? Is there any Python library which can do all this stuff for me if I give a dot wave file? So that's what was my question. Is there any Python library which can do this feature extraction, dominant frequency, calculation of dominant frequency, and fundamental frequency of a dot wave file given as an input?
So I think you can post your email, and then maybe you can connect to some experts who is actually using these different kind of Python libraries. So we'll be happy to connect you.
Okay, sir, done. Okay, sir. I'm
Thank you.
sharing my, sir, what should I do? I am sharing my email ID right now.
Yes, your name and email ID you can post in the Q&A box. Then we will, from there only, we'll able to help you to connect with some expert from us.
Okay, done, sir. Thank you so
While
much.
sharing the mail, also add your specific query.
Yes, yes,
so that
definitely.
it will be easy for us to understand, identify later.
Sure, sir. Sure, sir. Thank you.
Thank you. Thank you.
Yes, I would like to add a small note, maybe not very valuable, but can come handy sometimes. So, for example, in the panel, we don't have any experts in the speech recognition. That's why, we are trying to find and connect to the suitable experts. But in general, for all those grad students who are working in these areas, it is always advisable to look at some of these great leaders in the field, right? All of us have websites, display our work, and provide open codes and tools developed and all, right? So it is always a good idea to know who are the experts in our area and try to keep an eye on them, what sort of directions they're going in and what sort of tools they made it public, right? So having this done at the very early stage of grad days is very, very important. So if there are any students who out there who are entering into research and all, so this is one of the primary things you should know. Who are the leaders in the area? What are the directions they are also looking at? So some very useful information. Thank you.
Okay, sir. Yeah.
May I also add in that context? Yeah, hello?
Yes, sir. Please go ahead.
Yeah. So one thing which I would like to say is that, I mean, when you're talking about fundamental frequency and things like that, it's better to do a implementation by yourself. Okay. Because finally, if you just rely on toolkits, right? I mean, it may not go the long way unless you understand the concept. Okay. So
Yes.
I would suggest that you implement it yourself, okay, and then verify. Okay, of course, toolkits are available, right? So
Yes.
if it's something which can be implementable, right? I mean, you should try it out and make your hands dirty, right? I mean, then only you will understand, the concept much better, actually. Because
Yes,
toolkits are all tailored to a particular application, and then instead of breaking your head how to, modify it, right? And then if there is a slight tweak, if you're not getting the result, you're stuck, actually. Okay. So
Yes, sir.
my suggestion is to implement it first and then compare it against I mean, I'm not sure of the answer here, but the library, I'm not sure. But yeah, I mean, if it is something that's implementable, I think you should go ahead and implement yourself rather than relying on a toolkit.
Okay, sir.
At least for the application you're talking about. Okay.
Yes, sir.
Yeah.
Yeah, hello, sir. This is Nitika. Can I raise my query if allowed at this moment? Am I audible? Can I raise my query too?
Yes, please go
Guwahati,
ahead.
please go ahead. Yeah.
Yeah, actually, I'm working in a connected car domain where connected car information is received, and I want to actually figure out anomalous driving behavior by analyzing the temporal sequence. So at this moment, what I have done, actually, I have combined LSTM autoencoder with one class SVM model, but I am restricted with the libraries which are already available either in Python or R Studio. So I have implemented this and got some results as well. But at next level, actually, I wanted to customize these models, mathematical models, and maybe I would like to modify the kernel function, which is part of the OCSVM techniques. So I am not getting any headway, like because these are the standard libraries. How do I actually integrate or modify the custom implementation and modify the base algorithm itself? So in case there is any research or any direction which is or reference material which helps me in this area, so that will be really great.
So Nitika, do you have so your code is open source, some Python library, or it's some closed source code that you're using?
I have used closed source. Basically, it's a Python library which I have used. I have used mainly Keras uh, and for support vector machine as well. There are certain libraries available in Python, and for LSTM autoencoder as well. So some libraries are available. So I have utilized those only. So though I am been using one technique for hyper tuning, I mean hyperparameter tuning, but the base model or algorithm I am unable to change actually, because this is custom. This is not customizable. So this is basically inbuilt libraries.
So I would suggest, if possible, say you are doing research or some project, so most probably it is better to try out, open source codes. What happens is that, say there's some implementation in Keras or in TensorFlow in PyTorch. What happens in open source codes, for example, say you get from GitHub. So actually you can look into the code and modify itself, right? So like SVM code, it's better to write your own code, or maybe actually utilize some existing open source code that you can find it, for example, GitHub, with proper license that whatever you are looking for, and then actually go and modify it. So it should be possible. But if you are really tied with some closed source code, or some code that you cannot modify, it will be a bottleneck in your project, because ultimately you want to create some novelty and then new ideas, and if you cannot modify, you'll be stuck. So I would suggest that, or you also explore some alternatives, open source alternatives, where actually you can go and modify the code. So that's what from my side I'll say.
Okay. Thank you.
You're welcome.
Yeah, one more question. Is there any mathematical modeling reference for say support vector machine technique, which Suresh sir covered today morning, and the Bayesian learning technique as well? So is there any reference material which we can actually review it at later stage? As of now, I think some of these concepts are relatively new. So if we can actually go through those concepts, so it will help us in understanding the mathematical modeling little deeper.
So what I covered yesterday was primarily from the book Pattern Classification. Okay, you can write it down, or probably I'll put it in the chat box. Okay, by Guwahati and Stark. Okay, and is it fine?
It would be better if you can give it in the chat box.
Okay, just let me. So where should I? To all attendees, right? I have to put it there, I think.
Yep.
Yeah. So I'm just typing. Okay, is it fine?
Yeah, sure.
I
Thank you
think
so
the
much.
edition would be probably, I mean, I have edition 3 or 4, probably now it would have revised, so you can just check.
Sure, sure. Thank you so much, sir.
Mr. Biplab? Hello?
Yes, sir.
So maybe we are already like 8 minutes past our schedule. Maybe if there are no more questions, probably we should move to the next session.
Yes, sir. So, sir, our expert will be joining soon. We will be giving 5 minutes break to all the participants. After 5 minutes, we will start the session.
Okay. Sure.
All participants, please stay. Don't disconnect.
Yeah, and if there are further questions, maybe they can post in the chat. We can try to answer it later.
Yes, sir.
Okay, thank you.
So I will leave the meeting then. Okay, fine. Thank you.
Thank you.
Yes.
Sir, thank you.
Good afternoon, sir. Can I ask one little bit question, sir?
Subramaniam, sir, am I audible to you?
Yeah.
So, sir, I am making with a presenter.
Yeah.
Participants have been given 3 minutes of break. They will be back and we will start the session, sir.
Right. Okay.
I hope all of you have returned from the break. Today our let's start our next session. We have with us Professor R.B.V. Subramaniam sir, Chief Investigator of E&ICT Academy, NIT Warangal, and Professor in the Department of Computer Science and Engineering, NIT Warangal. His area of interest includes data mining, big data analytics, fuzzy data mining, spatio-temporal data mining, distributed data mining, graph databases, and machine learning. Sir will be taking lecture on regression and classification. Over to you, sir. I'm handing over the session to you.
Thank you. Thank you for your nice and brief introduction. Yeah. Good morning, good afternoon, everybody. It is my privilege opportunity to deliver 1 hour lecture on classification, possibly on regression. And I think there is another part of the same topic which will be handled by another speaker. Just I would like to know whether the other part is over or I am the first person speaking class on classification.
Sir, you are the first person. The other part will be on linear regression, sir.
Oh, he is also on regression. Okay, then I leave complete regression to him. The classification. Yes. Classification is a knowledge which is required to perform a task called classifying the objects. Hence, in classification, there is something classified. Hence, classify is a task. When I say classify the objects, you should know how to do that particular task. This FDP is on machine learning. Hence, we want to make the machines to learn like human beings. Hence, human beings, they perform tasks, several tasks we do. Any task, you take something like driving, cooking. Hence, you can go and give the example, swimming. These tasks, we perform it in a better and better manner as we gain more and more experience. Hence, as you gain more and more experience, if you measure how you are performing the task, that measurable value will also increase with experience. Hence, we expect machine also to perform the task in this manner. But here, what do we mean by experience? Since we use this experience word in some contexts. Some people, if I ask, what is your experience? They may say in terms of years. I have 10 years experience, 20 years experience, something like that. Or they might have undergone something. Suppose you have visited some place, and if I ask what is your experience, yeah, it is a wonderful experience, or it is a better experience, something like that. And here, what do you mean by experience with regard to the task? That is one thing which we have to discuss. Hence, the experience, when you are experiencing something, or in service when you are gaining the experience which you are generally telling in terms of years, basically you are exposing to the objects. Hence, in your 10 years experience, 15 years of experience, you are increasingly seeing the more and more people. You are handling more and more objects of the concerned world. Is it not? Hence, when you have teaching experience, means you teach many courses, you teach sometimes the same course many times in better and better manner. Hence, something when you are experiencing means you are exposing to the certain objects in the concerned world. Hence, it is mostly in terms of the number of objects. Hence, someone may have worked for 20 years, and suppose he has not seen many objects, he has not discussed with many human beings, he has not taught at all many courses, then it has no meaning at all. Is it not? Suppose you are a person who can understand the human psychology. If I talk for 5 minutes, I can assess a person. Suppose you say that that is your capability. How you gained it? It is because you have interacted with many human beings. There may be another person for 10 years he is in that field, but he has seen only hundreds of people, whereas you have seen thousands of people. That thousands of people matters. Hence here the experience means the number of objects in the concerned world. Because how we gain the knowledge only because of our interaction or our observation over the objects. Hence here the experience you have to take in terms of objects. And then the next question is, how do we introduce the objects? Hence, your parents perhaps they have introduced certain objects in your home, and your friends have introduced some other objects in the society. Your teachers have introduced certain objects. Okay, the objects are distinguishable entities. Fine. Yeah. Now, when your mother is introducing objects, say for example, she would like to teach you about vegetables and fruits, what she will do? She will show you a vegetable and asking you to look at it. What do you mean by looking at the object? You may be looking at the shape of the object, or she may be very particular about asking you to look at, see boy, look at the shape of this object, and maybe you taste it. This is the taste of the object. Or you may be asked to look at the color of the object. Hence, these are all certain things which your mother may be asking you to look at it. Hence, whenever you are looking at that object. Hence, thereby, one particular object is being introduced to you. Hence, one object having some specific shape, some specific taste, and some color green, something like this. This is how they introduce the object. Okay. Hence, these things which we consider here are known as features. Hence, perhaps some lectures have already taken what do you mean by the features, why features are important. Hence, here for each object, what I am taking, the values of the objects. Values of the objects. And these values of the objects are the facts. The facts. Shape is a fact. Taste is a fact. Color is a fact. For you person, your specialization is a fact. Your UG degree is a fact. Hence, what I am noting down are facts about entities. It means the data. Hence, data. Hence, data is collection of facts about entities. Hence, we are giving you the data. The values of the features are considered as data. For each object, we are giving a tuple here. Thereby, I say one object is introduced. And I will take another object and I will introduce its data here. Like this, we get a data set. And here, each tuple is representing an object. When I say you have to have more and more experience, as you gain more and more experience means as you see more and more objects, it means as the data is increasing. Hence here, in terms of experience means your data should be huge enough to understand those objects concerned. That's how we have to look at it. This is how the data became crucial for a mission to learn. Hence, if mission has to perform any task, it has to learn from this data only. Hence, what it has to learn to perform a particular task, it changes from task to task. Hence, here I am taking the task called classifying the objects. Hence, classify the objects. That is my task. Hence, I am asking, come on, classify the objects. Now, what do you mean by classifying the objects? If I say, what do you mean by eating? What do you mean by swimming? What do you mean by driving, cooking? You know the meaning of those tasks. Now, when I say classify the objects means what? What we have to do? Classifying the objects means specifying the class. Hence, specifying the class. Specifying the class to which the object belongs to which the given object belongs to is known as classifying the objects. Hence, classification is a knowledge required to perform the task classifying the objects. Classifying the objects means specify the class to which the given object belongs to. Hence, if I show you an object and I'm asking you, come on, specify the class to which this object belongs to. Hence, you are saying, sir, this object is chalk piece. It means you know the name, the class to which this object belongs to. How you came to know? Someone has introduced you. Hence, it is not just by birth you came to know. Someone has told that this object is already given some name, chalk piece, and you should also call with that name chalk piece only. Whenever you want this object, you have to ask, give me some chalk pieces. If I ask, go and bring chalk piece, you should know what do you mean by chalk piece. Hence, that's how you should know the names given to these objects already by other people or by our ancestors in the society. That's why your mother also introducing the vegetables. Suppose there is some object, say something like red, and if this fruit is apple, hence you should know that this red colored, some taste, shape, this kind of fruit is called apple. The same thing, again, if you want that fruit, you should call with apple. If someone asks what is this fruit, you should tell apple. Hence, apple is the class name given to the objects. Okay. Hence, when you want to specify the class of the given object means you perhaps know the class name prior to this question. Is it not? Hence, you might have undergone training, maybe under your mother, father, teacher, friend, some peers, someone has helped you to know the class names of the objects surrounding you or in the concerned field. Suppose you are working in some field, maybe there are some artifacts, there are some objects, you should know the names of those objects. When you are working in electronics industry, you should know what are those electronic spare parts and all. If you are working in software, you should know what are different softwares. Hence, like that, each person has his own concerned world. Hence, in that world, there may be the objects are already given names, and those class names should be known to you. To know that, you perhaps undergone some training. Training with the help of some supervisor. Someone who is introducing the objects is known as supervisor to you. Your mother is a supervisor, father is supervisor, so on. There are many other supervisors in the world for you who introduce these objects. Okay. Hence, we are talking about one kind of learning. Hence, what you are learning now, I am giving you the data. Hence, from this data, you are learning as a human being. Similarly, mission also is expected to learn from this data. Okay. Hence, with the help of the supervisor, and what it is doing now, it is trying to learn about labeled objects. Hence, these are all labeled objects. Hence, each object has a class label. Hence, now, therefore, in this data specifically, which I call it as it is equivalent to your training, it is training data. I call it as training data. It is equivalent to the training what you are receiving under your mother or someone who is introducing these objects. What it will contain? It will contain values of the features as well as the class label of the object. Hence, there are certain features, something like F1, F2, so on, Fn, and there is a class label. Now, during this training, you are getting exposed to various objects. Thereby, you will come to know certain number of classes. How many classes you are learning? Maybe certain finite number of classes. Hence, m number of classes. Apple is a class. Chili is a class. It's like that there are m number of classes which you are undergoing, you are getting exposed to during training period. Okay. Hence, now once this kind of training is given to you, then once the training is over, then you are in a position to face a test. What will happen in the test? In the test, I will take an object X, I will give its shape, I will give its taste. Hence, all the values of the features will be given except this class label I won't give. During training period for each object I used to give the class label, but now during testing I will not give the class label. What you have to do? Now you have to specify the class. Then specify the class. Specify the class to which this X belongs to is the question. Hence, I am showing you an object. Come on, specify the class of the object. I am showing means for you, you can see it. You have eyes and you can listen when I am describing the object. Whereas for the mission, I have to give the values of the features. Hence, once the values of features are given, mission should specify the class to which it belongs to. What will be the answer? Answer is, expected answer is one of these C1, C2, Cn. Because mission knows only m number of classes. Because it has undergone the training, it has exposed to m number of classes. Hence, it knows the objects belonging to these m classes only. Hence, answer, if at all, if this X is one of such objects, then it will recognize one of those C1, C2, Cn. Something like, if you know some 10,000 vegetables and 20,000 fruits, and if I show you some fruit, if this one fruit which if is already known to you, then only will specify the class. Suppose I bring one fruit from some other country which you have never saw it. Then can you name the fruit? You will simply say, I don't know. Then someone will say, no, this is the fruit, its name is this, I brought it from sun. So you see, come on, these are the features. It means now one more fruit is added to your knowledge. Hence, your knowledge that is classification, is getting exposed as you see more and more fruits and vegetables in the world. That is what, with more and more experience, you can perform more and this particular task of specifying the class in a better and better manner. Hence, compared to your own child age, maybe at that time you know very limited number of fruits and vegetables available in your village. As you grown, as you have seen and visited many countries or many shops in the town, then slowly you came to know many other vegetables and fruits in India and in this world. Is it not? In many other countries together. This is the problem. Hence now, I hope the problem is clear to you. For a human being, training is required. During training, you will be exposed to the objects. Equivalently, for the mission, I am taking the training data, which means for each object, there will be values of the features as well as the class label, because I am trying to make the mission to have the knowledge about labeled objects, and the knowledge about labeled objects is always obtained because of the training data, and hence this kind of learning is called supervised learning. In this supervised learning, we are taking a particular concept where we would like to make the mission to perform a task called classifying the objects, specifying the class, and how it will specify only if it has seen certain number of class objects of certain number of classes. Once it has learned from this data, then it will be in a position to specify this. Now the question is, okay, anyway, we are recognizing vegetables and fruits. Why mission has to learn this? Why mission has to specify the class of the objects such as vegetables and fruits? It is not just for the fruits and vegetables. You can think of many other applications. Even in the airport, when you look at what security person is doing, the security person is doing, looking at the bag, opening the bag, and he's observing what are the objects. It means he is recognizing, oh, this is toothpaste, this is a towel, this is soap, and this. Okay, he is naming these vegetables. He knows these objects and the class of the objects, and he's saying that, okay, these are all permitted. Okay, fine, you can carry this bag. Hence now, if instead of that security person, if I keep a mission which is also aware of various objects generally which we carry, and then it will also look at the objects, it is scanning and identifying these objects. If I can provide that capability of looking at the objects, then by looking at the features of the objects, it can now specify the class of the object. Thereby, it can permit a bag to carry with the person or not. The advantage is now you are replacing a human being with a mission. Mission won't get tired. You can replicate as many counters as you want. It's like this. It may be in future, it may happen that already it is taking place now. It may be instead of shape, taste, color, I may give the symptoms of the patients. Hence, each object is a patient, and for each patient, I will note down the symptoms with which he is suffering, along with some other features or maybe the parameters indicating the body, something like oxygen levels, BP, this, that. Now, once these features are given, the class label can be the name of the disease with which he is suffering. Suppose I give this kind of data. This is what the doctors are undergoing. Hence, during the medicine course, what they do, they are exposed to various patients, their sufferings and their symptoms, what kind of body parameters they vary, and they associate one kind of patient, they will diagnose that he is suffering from so and so, disease, and then his senior doctor will tell if this is the disease, this is the medicine that we have to give, all these things. Hence, now first of all, each patient is basically getting classified. Hence, once the training is completed, if mission also can understand like this, if mission also can learn, and if I take you a new patient X having these symptoms and the body, then what is the disease that he is suffering from? Mission will tell. And instead of the name of the disease, suppose here I write the diagnosis, suppose what kind of treatment has to be given, then the treatment may be give penicillin and give that tablet, this tablet, suppose these are some 3 or 4 actions, and those actions if I write in terms in place of class label, then once the mission looks at this patient X, observing its that person symptoms and the body parameters, then instead of naming the disease, it can straight away give instructions to the patient or to the nurse, so that if you follow the instructions, the disease will be cured. Hence, we may get such kind of systems tomorrow. Already in some places, somewhere, some assistance to some extent it is giving. Whether a mission will independently deliver as a doctor or not, that it at times takes. But already doctors are taking the assistance in arriving at some conclusion. Is it not? Now, once in the name of the class, if you can write the instructions straight away for the X, those instructions will come. Hence, that's why in some books, people say that in the supervised learning, what we get instructive feedback system. If you train up some system under this, then instruction will come from the system. Hence, what medicine has to be taken will come from the system. Hence, instructive feedback is the kind of system that you can build with the supervised learning. Whereas in the reinforcement learning, see, instruction is coming, means whenever you want to perform some action, the instruction will come from the supervisor. See, at your home, suppose you are cooking, what you do, what is the next thing, what action is that you have to put now? Should I add salt or should I add mirchi, this, that? No, your mother is telling. Similarly, at college, whatever you want to perform, your teacher is telling. Therefore, when you are training a system in the supervised learning, always systems gives instructions about the actions to be taken. Means whenever the agent has to take some action, the agent cannot take action on its own. Always instruction comes from the supervisor. Okay. Hence, the systems which are working with supervised learning systems, the actions are dictated by the system. Agent has to simply follow that. Whereas in the reinforcement learning, action will not be informed by the system. You do whatever action you feel, which will be deemed to fit for that particular situation. But your actions will be evaluated. Suppose no one is teaching you, no one is helping you. Then, okay, given the situation, suppose you are somewhere and you ask, sir, what to do? No, I won't tell. You do whatever you like. Then, okay, you will perform something. Though you are given the freedom to perform something, but the action what you have taken will be always evaluated. And evaluative feedback will come. And in the reinforcement learning, this evaluative feedback will help you to learn about what actions are good, what actions are bad, whether you want to repeat those actions. These things you will learn it. Thereby you will learn how to get reinforced into the new environment. Suppose you are a person living in the village, you have a cycle or motorbike, Okay, in the motorbike, you ride very freely, no restrictions in the village, you can roam around. No one will object. The moment first time if you enter into the new town, nearby town, Kolkata, Guwahati, you as usual know the way that you used to behave in the village. Here also you will ride the bike just into the town. You are crossing a signal line where there is a red signal. You don't know that you should stop there. You have simply crossed it. Hence, at one particular state, that is at the junction, we have decided to just cross like that, though many others have stopped. Why these people are fools? They have stopped. Let me go. I used to go in my village, hence I will also ride. When I cross that, hence it means you are given the freedom to perform action, whatever you feel, whatever you want. But once you have crossed it, a police person will come and hold you. He will say that you have done a mistake. Come on, pay the fine. Then you can't argue that, no, I don't know. It's not the question of no one will teach you here. There's no supervisor. You have to learn on your own how to live in Kolkata, how to live in Guwahati, how to live in Rome. Hence, be Roman in Rome, no? Be Roman in Rome. Hence, you can't be like an Indian in Rome. Hence, you have to learn how to be a Roman in Rome, how to be a person living. There are many other persons living in Kolkata. Hence, you should also learn how to behave like a citizen in Kolkata. Hence, you can't argue that the mayor of Calcutta should have taught all these things. No one will teach. There is nothing like supervised learning. Hence, here, for your action, there is some evaluation has come. The evaluation is in terms of collecting fine from you. Oh, then you will realize, okay, next time I should not do this because I will lose my 100 rupees from my pocket. Okay, next time whenever I see the red signal, I should not do it. Hence, it is not always instructive feedback supervised learning system help the person to gain the knowledge. On the other hand, this evaluative feedback also will help you. Thereby, slowly, you will learn how to live in a new environment. You will get reinforced into the new environment. After 3-4 years, slowly, you will become like a person, normal person in the Kolkata. It means you got reinforced into the new environment. That's a reinforcement learning. Okay, fine. Now the problem here is the classification problem is it comes under supervised learning. It is about the knowledge about the labeled objects. Why the knowledge is required? If you have the knowledge, you can specify the class of the given object. The specifying the class of the given object is called classifying the objects. That is with the help of the knowledge classification. Okay, now how you will perform it, how you gain this knowledge. Hence, the task is clear, problem is clear, and now the question is, okay, though we can't provide a mother or teacher to the mission, okay, in one way we have provided training data. Now, mission has to learn from this data. Now, what it has to learn? What it has to learn? So that this task, that is specifying the class of this object, can be performed. That is now the question. Okay. Now you look at this training data. What it contains? Oh, it contains, you look at, carefully look at this training data. One object is chili, one object is apple, another object is tomato. This is also red. Yet another object is potato. There are so many fruits and vegetables. And this is given in this data set. Now it has to learn something from this. That learning should help to perform the task. That's the problem. Very simple. Okay. This which you are performing as a human being. Now it is not the question of you understand how you are performing, but you have to now train the mission so that By training the machine means we are allowing the machine to learn from this data and perform this task. That's the question. Okay, fine. Now how it will learn, what it has to learn to perform this task is the question. Okay, yeah. Now for this, you think how your mother started teaching you about the vegetables and fruits. Here also I am saying same thing. I'm not bringing any big problems here. See, your mother has affection, no? She taught you without confusing you. She's a good teacher for you. She's the first best teacher for you in your life. Everyone considers his mother or parents. No, they are the best teachers. They have introduced the world to you. Now, without creating any confusion, vegetable by vegetable, fruit by fruit, object by object, it is introduced to you. Sometimes even when you confuse, she cleared the confusion. She expected that confusion is happening in your mind. She used to clear it. In the same way your teachers taught you. They know. Sometimes you got confused. They will clear. I know you misunderstood it or you are in confusion state. See, this is how I will clear the confusion. They will repeat it. They will express in some other way. Finally, they will teach in an ambiguous manner. Hence, that is the supervisor. That is the teacher's capability. Unfortunately, in this training data, some problem is there. What is that problem? I am giving this entire data at a time to the machine. Okay, giving at a time, is it a problem? No, not really. That's how I am in a dialogue way I am teaching you. I don't want to give object by object. Okay, I have given enough data, some 1 million objects. For each object there is a tuple. I need not explain again. This much data is given to the system. Hence it is about the objects which are chili, apple, tomato, so on, so many fruits and vegetables. The M number of classes, M is sufficiently large, maybe 30,000, in which 10,000 vegetables, 20,000 fruits. Now from this it has to learn. When all is given at a time, just I will give. If I say what is problem, you will only tell that, okay, training data is given, sir, it has to learn from this and then specify it. You will repeat only the problem what I have said. Hence now I will take you to one step ahead. I will say the problem in this data is it is a mixture of several objects. Hence I gave you a mixture of objects belonging to various classes. It is not same only one set of only apples. No, I have mixed up apples, tomato, chili, everything. Like, in olden days, our parents used to bring in one cloth bag all vegetables, fruits from the market. Weekly once they used to conduct some market in the village. They will go there nearby town and they bring, yeah, like that. It is a mixture now. Mixture of the objects. Now, when such a mixture is given to the machine, what is the problem? Any problem with the mixer? What you will attribute? Sir, if mixer is given, this is the problem. You think of whatever the problem you think in your mind, what you will think that it is because of the mixer the problem is arising. And that problem should not have arisen had I not mixed up. Hence, can you cite such a problem? Anyone, you can unmute yourself. Whether such permissions are given, people can interact with me. Now, someone can tell what is the problem when the mixer is given. Someone on the E&ICT Academy, Guwahati, can you assist me? Is it possible for the participants?
Trying to unmute all, but all participants are requested to keep their audios mute until they ask any question. Actually, all of them get unmuted.
तुमच्या अधिकाराचं तुम्ही बघा मारा मग माझ्याकडे पाठवा मी त्याला अलाव करतो
पेमेंट आज
Please mute all the people.
सॉरी मला कामाचा रिझल्ट पाहिजे बाकी
सर नहीं आले रे अजून आहेत वरती येतील सर
सुबह वहाँ पे एम्बुलेंस था वैसे आंसर प्रश्न वन आंसर
केलंय केलंय हो 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 झालं हो 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 केलं तेव्हाच केलं पण तुम्हाला मेसेज नाही दिला केलंय येस एकदा चेक करायला
अरे दोघांनी ना आज सोल्डरिंगला मदत कर वो जीएसएम लाया है हमने वो मैडम कुछ बोल रही थी ना वो इमेज डाउनलोड करके
कनेक्शन कनेक्शन
कनेक्शन के लिए
सर्किट डायग्राम
All participants are requested to raise your queries in the chat box because once we unmute all, it again creates trouble.
Can we mute?
Yes, sir. We're trying to mute from our side.
What we do is for each one you can mute. Yeah, give us co-host otherwise. Yeah, they already made host.
Dunga, you need to just mute yourself. Mr. Dunga, what?
Dungavat Naik, Dushyant, yeah.
Sir, all are muted now.
This is what is happening.
Yes, sir. In the event, it is happening like that.
It's only one way kind of thing. Yeah. Yeah. Okay. Hence, hence, if anyone can tell the problem with the mixer, of course, this is what happened when we take a mixture of the participants, some who are interested, some are not interested, some are listening, some are not listening. This is the problem of the mixer. Hence, when the mixer is there, say for example, you take milk and water, mix it, you have got a mixer. What it is? Is it milk? No, milk got mixed with more water. Is it water? No, water has got mixed with the milk. It is neither milk nor water. You got a different liquid, which we call it as a mixer. Because of the mixer, milk has lost its purity and milk got impure. Hence now it is impure milk, it is impure water. Hence impure milk and impure water, hence impurity is gained. When you mix up, impurity has come up. Hence in mixer you will have impurity. In this example you can use the word, when you mix up two liquids, you have got both impure and you have got some amount of impurity. Hence the problem with the mixer is impurity. Then how to overcome it? You reduce the impurity. You reduce impurity. How much I should reduce? Tell me how much impurity is there. Hence you find out the magnitude of impurity, that is how much is there, quantity of impurity. Hence if you can quantify, hence if you can measure the quantity of impurity, measure the quantity of impurity and try to reduce it to zero. Reduce quantity of impurity to zero by some process. Hence you have taken this mixture, you have to measure the first impurity and suggest some process whereby I will slowly reduce this quantity of impurity and finally I will show that, see, now impurity is zero. Hence once if it is impurity is zero, then your problem is gone. What is problem with the mixture? Impurity. This impurity, once if you can reduce it to zero, you are successful. Hence how to convince you that there is no more problem? It is again I have to measure. Hence every time during the process and the end of the process, I should measure the impurity and show you that, see, impurity is gone, has come down to zero, therefore you are perfect, you are pure. It's the same thing. Suppose if I go and someone says that there is impurity in my body, okay, they will apply some medicine and slowly finally they will reduce the impurity in my body, and then finally will say impurity is 0, you're all right. Hence, in the same manner, shall we investigate and suggest a process which will bring this impurity level to 0. At the same time, I should also have a device. How do I measure the impurity at any time in the given data set? Hence, there are two things. One is, how do you measure impurity in a given data set? If impurity is non-zero, then how do you reduce it? That is the second thing. Hence, how to measure impurity, how to reduce the impurity. These are the two things required. Okay. Hence, that I will consider now and try to apply it on this mixture. Okay. Hence, in some other examples, okay, sir, this example is bringing the word impurity. What else possible? Yeah, in some other example, if you take, instead of the impurity word, you may feel that ambiguity is the right word. When you mix up something, you will have ambiguous kind of thing. Suppose there are two things mixed up. Oh, there is ambiguous thing. It is not clear. There is ambiguity is there. Hence, ambiguity, some state of confusion, some impurity. These are the maybe relevant words which will fit for different contexts. Hence, whether it is impurity or ambiguity, whatever it may be, these are the general problems that you will face when you consider any mixture. Hence, yes, the data is mixture. Now I am considering, I am stick to one particular word, impurity. Okay, fine. Now, how I can reduce impurity? Okay, let us postpone one point, that is how to measure impurity. This you know very well because most of you are from the ECE background. Hence, measuring impurity is one task. Second thing, reducing impurity. Now I will attack the second one because some of you know how to measure impurity in a given data set. Anyway, I will come to that first. Hence, how to reduce the impurity. Hence, just now we said the impurity is risen because of the mixture. When I mixed up milk and water, the impure liquid has come. Hence, how to remove impurity means you demix it. Hence, how to reduce impurity? Reducing impurity should happen because of the demixer. Hence, demixer is one suggested process to reduce the impurity. Hence, you have to demix it. Hence, you have taken a mixer, you demix it. Okay. Hence, how to demix it? It may be sometimes it will be tough task to you. Suppose if I mix up water and milk, and if I ask come on demix it, maybe many of us we don't know, and even if you are a child, then you may say no, we have to bring something called swan, hamsa. Only hamsa will take only the milk and leaving the water. No, it is taking milk inside, and so milk is in its stomach, water is left over. That we don't want. We want to separate it. And then if you are a good person, then you will think, no, sir, it is easy possible. Yeah, you put it on a stove and then liquid will come out as vapor. Water has gone. The milk is low. No, I want both water and milk. I gave you 100 ml water and 100 ml milk. I have mixed up. Again, you have separated it and give me both 100 ml water and 100 ml milk. Okay, you will find out something, how to collect vapor and collected vapor converted to water, the leftover milk, something you will find, and there may be some loss. You may reduce the loss slowly by different mechanisms. Let us not go into that. That kind of demixer, is it what I want? And here these are the objects. The objects are having shape, taste, color. Now this object has some shape, the other object may have same shape or different shape. Hence now different shape objects perhaps there. Objects having different tastes may be there. Objects having different colors may be there. Hence now, can I demix it on some feature? Suppose I give these objects which are in a bag, I will pour it on the ground. If child don't know the names and all, first I will ask the child, you separate based on the color. And she will look at, if two objects are of same color, she will put in one, different color, she will put it in different. Hence, this particular data set, if I ask you to demix it, on color, hence on color, you are trying to demix it. What will happen? All green color objects will come into one set. Say D1, here you have D getting demixed based on the color. All green colored objects collected D1. All red colored objects are collected into D2. Like this, suppose there are 4 colors, yellow and white, and only 4 color. Let us assume there are only 4 colored objects are there. Then this original data set got demixed. It means it got into segregated into 4 different data sets. Hence, this kind of D1, D2, D3, D4, that D got into partition. This O1 may go into D1, O2 will go to red, D2, O3 also red, therefore it will go to D2. Like that, it got segregated. 1, 2, 3, 4. Now you will ask, sir, why you are asking me to demix it on color? Why not shape? Okay, instead of color, suppose I say, based on shape you demix it. Then all spherical may be got into D1, another color shape, yet another shape, D2, D. Hence S1, S2, S3. Only 3 different shapes are there, suppose. Then this D will be splitted into D1, D2, D3. Fine. But this D1 is different from that D1. This D1 is all green colored objects. These are all S1 color, S1 shape objects. Hence you got D1, D2, D3. But now the question is, which feature should be considered first? Should I consider based on the color and the shape and so on? Okay, even if I do it on color, now I got all green colored objects. I have got a data set. This data set is a sub data set of D. This is also a data set. Is it pure? Is it pure means you measure it. You know how to measure. If you measure the impurity in D1, if impurity is 0, you can stop. You need not demix it. If impurity is 0, hence if impurity in D1 is 0, you stop here. If impurity is non-zero, it means you have to continue this process. What process you can continue? Is it again required to split on color? No, already color, all green colored only got. But among the green colored objects, There may be different shapes. Hence, after color, after obtaining all green colored objects, now you may be segregating them based on the shape S1, S2, S3. Then this D1 further divided into D11, D12, D13. Measure the impurity in each data set. Here it may be impurity is 0, stop. Here impurity is non-zero, continue. What you have to do? You may have to split on test. Again, split it. Yes, first I have started on color, then shape, then some particular branch is getting stopped. Why it got stopped? No more impurity. Impurity became 0, whereas in D12 there is impurity, therefore further segregation I am doing it. Hence this, if you look at from this direction, there's a tree kind of structure is being developed. Hence this particular process of demixing is giving you some tree kind of structure where ultimately some branches, no, here this branch is got stopped because it has got impurity 0. Once impurity is 0 means it is pure. It means they all belong to same class. Same class means what is that class? Maybe C3. Here D13 also, suppose impurity is 0, this may be C4. Whereas once if I do it on the test, suppose here I get all purity, that is impurity 0, then here I may stop. It means it may be C5, it may be C6, it may be C8. The same thing may happen along the other branches. Hence it is now a tree kind of structure, ultimately having the leaf nodes have classes. Once this kind of structure is obtained, now this is what we say that we have learned from the data. This what it consists of. Basically, if I investigate, it consists of patterns. Pattern is collection of similar objects. Yes, the collection of green colored S1 shape objects are C3. Green color S2 objects having so and so taste is C5. This collection of similar objects, these are all patterns. These patterns are being formulated here. Hence, this is a something collection of patterns which are embodied, but that collection of patterns forming a cohesive structure, the structure looks like a tree. Hence now this structure is looking like a tree, and this structure now this is deciding the class of the X. How it is deciding? Now you see here, suppose here it is red color, your X is red color, then you should follow this, and then further if its shape is so and so, you have to come down. If its taste is that, then you will be stopping. Hence this X if you take, with X you will be traversing along some branch and finally you will be stopping at some leaf node. And whatever the class is there in the leaf node, that you can specify here. Therefore, this tree, this investigation process is helping you to name the class of the X. Hence, this kind of demixing is helping you to have collection of patterns which are forming a tree kind of structure. This kind of structures are called models. Hence, what we have done, we have learned to build a model, and that model is being used to specify the class. Okay, this is one approach which you can apply when your task is specifying the class of the object. And measuring the impurity, you know, the entropy, most of you are aware of, the entropy gives the amount of impurity in a mixture. Hence, always you find entropy. If entropy is 0, you stop it. It means it is pure. If entropy is non-zero, you continue this process of demixing. This is what I would like to tell of as far as the classification task is concerned. Any doubt? You can give it in chatting because I can't again dare to unmute you. And if you have no doubts, we stop here because now it is time to start another session, maybe after lunch break.
Hello.
Yeah.
Yeah, thank you, sir. Thank you for this wonderful talk. So on behalf of Professor Ratnajit Bhattacharya, I thank you, sir. And from behalf of all the academies, we express our thanks for delivering this lecture.
Thank you.
So dear participants, our next lecture will be taken by Dr. Irshad Ansari, sir. So before that, we will have a lunch break of 15 minutes. Ansari sir, are you there?
Yes, I'm here.
Sir, with your permission, can we have a 15 minutes break now, sir, as a lunch break?
Yeah, sure. Please.
Okay,
Yeah.
sir. Thank you, sir. So we will start the next session from 1:40 onwards.
Okay, fine. No problem from my side.
So dear participants, we request you to have a lunch break till 1:40. Hello, good afternoon, everyone. Is my voice audible? Thank you, sir. Sir, we have given you the presenter, right, sir? So you can share your screen and have a test run before the session starts.
Okay, I believe the screen is already shared and I'm audible.
Yes, sir, it's clear.
Okay.
We can see the presentation.
Yep.
Thank you, sir.
Yeah. Can you see the slide movement? Is it moving?
Yes, sir, we can see the slides moving.
Okay, fine, fine.
Yes, sir, we can see your video also. And your voice is also audible. Thank you, sir. Okay. So good afternoon, all. So on behalf of all the academies, I welcome you all in this second session of this 5-week faculty development program. So our next lecture will be taken by our next expert, Dr. Irshad Ansari, sir. So before the lecture starts, we will have a short introduction of our speaker. Dr. Irshad Ahmed Ansari, sir, is working as a faculty in the discipline of electronics and communication engineering at IIITDM Jabalpur, India since 2017. He received B.Tech degree in electronics and communication engineering from Gautam Budh Technical University, formerly UPTU, Lucknow, India in 2010. M.Tech degree in control and instrumentation from Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, Punjab, India in 2012. He completed his PhD from IIT Roorkee with MHRD teaching assistantship and subsequently joined Gwangju International Institute of Science and Technology, South Korea as a postdoctoral fellow. His major research interest includes image processing, signal processing, soft computing, brain-computer interface, and machine learning. He is senior IEEE member. He is presently guiding 3 PhD scholars. He has authored more than 55 research papers in various reputed international journals and conferences of publishers like IEEE, Elsevier, Springer, IOP, etc. He is also serving as an active and potential technical reviewer for various journals of repute. So with this, we welcome sir for this session. Over to you, sir.
Okay, thank you very much for introducing me. Today I am here to present you all with the topic clustering and how clustering can be useful as an application tool for the signal processing and communication engineering domain. So this is my email ID. Even after the session, if you have any query related to this field, you can contact me and I will try to answer to the best of my ability. Okay, so as overall, all together, if we see this domain, the machine learning applications, so they are growing very rapidly in the last decade or so. And the reason of the same is that now we have much more powerful tools as we were having earlier. So the processing abilities of individual as well as dedicated processors has increased significantly. And that's why the techniques that were there since last, you can say 40, 50 years has seen a rapid growth in application point of view. And that's why this faculty development program that we are doing is focusing more on the application rather than the techniques. So I will also keep that in mind, and accordingly I will try to introduce different aspects of application rather than the only basic concepts. But before going for the application, obviously a little bit information about the basics is also important, so we will follow that. If we see what is the purpose of this presentation, the outline is will be first we will differentiate between the supervised and supervised learning, and I know that majority of you already know this thing, so we will just quickly touch that thing. Then we'll touch the introduction to clustering part. Then we'll see k-means clustering, because it is a very basic form of clustering and how that can be used for various applications. And then we'll see what is the basics of the competitive learning, that is also a form of clustering algorithms, and how they are used with the help of a neural networks. So this we are going to see. And the basic difference between a supervised and unsupervised. In supervised, we have a teacher or we have a labeled data where I can see what I want to achieve. Okay, means I already know what is right. So if I already know what is right, so the things become much more simpler, because I already know where I'm supposed to go, okay, or what I want to achieve. So if that is there, it is a supervised form of learning when there is a teacher present. And the second form, that is unsupervised learning, which is more challenging when we don't have a teacher. So obviously, when we don't have anyone to teach what to do and what not to do, the option that we left with, we are going to do some trial and error based sort of thing, or we can do the learning as per our understanding. Means if I give you this data, as you can see over here, this data, okay, and let's say the colors are already not there. Okay. We assume that the colors are already not there, and it is just some random data. I'm just going to give, okay, this let me make some random data. If I ask you, okay, your aim is to just make 2 clusters. Clusters means the bunch of data, basically. Okay, the bunch of data you are supposed to make. So what you are going to do, you are going to create a cluster. There, different people might have different approach. Okay, one can say I'm going to cluster it like this. These 3 belongs to one cluster. These 3 belongs to one cluster. Another can say, no, I don't want this type of thing. I want to cluster it in diagonally. Another can say I can cluster this diagonally. I can say this type. So whatever type of boundary one can make, okay, because there is no correct answer, so you cannot say that that person supervised learning, because I don't have any labels, means what to do, I don't know that, but that is advantageous also. In many cases it is advantageous and give us a way to improve our knowledge. Okay, how? I'm just going to tell you. Because when you don't know something, there is always a scope to try and then improve. Okay, so that we can do always. Scrub this thing. Okay, so basically here what we see when we're going to cluster, so one clustering could be on the basis of distance. That is one possible way, means because you have some data points, so you can cluster on the basis of the distance. Means this smaller group I can cluster in one cluster, and the larger or the data points that are at distant location, I can cluster them in another group. So that could also be one possibility. Another possibility you can see right now on the basis of color, we have made two different clusters. So whatever is my approach, color, size, or distance, we have to choose one feature on which I can make the cluster. Or if I have better processing abilities, what can I do? I can make multiple features table. Means I have feature 1, feature 2, feature 3. I have this type of 10 features, and then I have using all those 10 features, I'm going to find out certain patterns, okay, that satisfy all the 4 features. So that I can do. Satisfy means in whatever terms in all the 4 features, the data should look like similar. Okay? Similar means they have similar type of colors. If let's say my criteria is black and white, so not completely white, but quite similar to white. If my one more criteria is the shape. So if let's say it is circle, so I need not exact circle, but quite similar to circle. So on these basis, what can I do? I can differentiate and I can make a cluster. Okay, now another thing is, what is the use of these type of clustering? Why even we are bothering and why we are trying to do something like that, where we are supposed to make a cluster? Okay, so one of the very recent example that you can see over here is the COVID-19 clusters in India, in our country. Okay, and as you can see here we have the case clusters. Basically, at which locations we have more number of cases, the larger clusters are there, and where we have a small number of cases, a smaller clusters are there. So overall, if we see this situations, this is one of the obviously application of a clustering. A good clustering algorithm is needed so that we can make a better cluster, so that the other people can avoid traveling to those locations where we have a larger clusters. Obviously, right now we are having this thing on the complete Indian map, so that's why it is not that useful. But if you made this cluster over every city, then this becomes much more useful, because then I have a location specific or area specific clusters where we have more number of cases, where we have less number of cases, and up to which limit I should make a cluster. I mean, what should be the boundary of my cluster from where the people should not go. Okay. So this type of, moreover, what we can do, we can and do the analysis how clusters are changing, how they are behaving, how new clusters are forming within the clusters. So multi-level clustering is also possible. So all these things can be done. Okay. And as you can see, John Snow in 1850 was the first physicians who plotted the cholera death on a map. And that was the first, one of the first application, you can say, of the clustering. And you can see the concept is very old, obviously, but now we have tools and now we have the processing ability. So we can tackle a large amount of data. And that's why it is now very much useful. Okay, so if we talk about very similar thing in terms of computer vision applications, okay, here we are seeing the image segmentation example, and image segmentation is also nothing but, you can say, a clustering sort of thing, where we are clustering the image. Because what we are doing, we are segmentized. We are breaking out the image into different parts. That's what we are doing. So let's say my aim is to segregate the image on the basis of color. Okay, or because it's a gray image, so I can say no, I want to break it on the basis of intensity. So let's say this is my intensity level 0 to 255, and I want to make one very simple clusters. So let's say I have decided, okay, 0 to 50, 50 to 100, and 100 to 255. These are my 3 clusters. So on the basis of this intensity, I'm going to have 3 different regions, and I'm going to mark them. Mark them means I'm going to set a fixed value. Means, for example, between 0 to 50, I'm going to set everything to 25. Between 50 to 100, everything to 75. Between 100 to 255, everything to 200. Okay, I'm just assigning it randomly. But in practice, we do have a criteria how to decide this value also, that we are going to discuss. Okay. So once you do that, obviously all the intensities that is belonging to 0 to 50 become 25, single intensity. So that become a cluster. Means all the pixels that have this range is now belonging to one cluster. All the pixels that are between 50 to some other region that was 100 is now having an intensity value of 75. So altogether, if you see, it is nothing but this is a formation of a cluster. So different elements now I can see, and not only on the basis of color. Obviously, every segmentation cannot be done on the basis of color only. Where we have very good segregation, already we can see that on the basis of color, we can use that, no problem. But if you see that that is not possible, you can make some other criteria. Means the features, you have to pick the features. What type of features are there that can help you to segregate? So that feature you are going to take and you're going to give that features to the clustering algorithm. Algorithm is going to make a cluster. Okay. So the clustering approach remains same. The only thing you are supposed to do is to choose a good feature. The better feature you are going to choose, the better clustering algorithm it is going to be. Okay. So this is another application, and obviously once the segmentation is done, you can have different parts of the image. For example, here, if someone asks me what type of vegetables are there. So if the very first thing for me is to segregate how many parts, different parts are there. Okay, so if I say, okay, 1, 2, 3, 4, at least 4 I can recognize. The rest vegetables are also there, but I cannot recognize them well. Or if the algorithm is good, I can say, okay, like I have 10 number of vegetables that I can see, and then I can segregate them. Okay, segregate them, and then I can put them into a classification algorithm further for further processing, where it can recognize also. So the very first thing is to segregate, then only I can recognize. So that's where this type of algorithm is very useful. So how do we basically do the clustering? Okay, so to do the clustering, there are 2 measures. Okay, one is the similarity, another is dissimilarity. Okay, so all the things that are similar. Now the question is similar in terms of what? So we have already discussed similar on terms of features, means the color, the shape, size, or any other features that we can think of. All those things we are going to collect. Okay. And we're going to create a data set out of that. And then I'm going to see the similarity measure, that is basically how much similar xi and xk are. Okay, so how to measure the similarity in mathematically? How can we measure? So in practice, when we are going to do any type of for example, let's say this is your feature 1, feature 2. So no matter what this thing is, ultimately, if it is a color, okay, or it is a distance, or it is some size, shape, whatever it is, ultimately the features are going to be some numeric value. Okay, where numeric value tells it is 6 feet long, that might be the case, or numeric value is telling that this is a blue color. So accordingly, RGB value I'm going to set. Okay, because it is a blue color. So some numeric value. Ultimately, everything that I'm going to have, the features going to be numeric, some or another form of numeric. That is only the possibility. Okay, I cannot have like color is blue, so I cannot keep it like blue. I have to convert it into the numeric equivalent, okay, so that the computer can understand, obviously. Okay, because everything going to be happen inside the processor. So that's why a numeric data is needed. We have to do that. Okay, so now let's say in the same way we have some features 5, 6, 2, 4, something like this. Let's say 8. Feature 1, feature 2, 2, 3, 4, 5, 6, 8. Okay, let's say something like this we have. Now, when here I am talking about S, Xi, Xk. So these are, let's say, my two features, and I'm calling it Xi, I'm calling it Xk. Okay. These are the two features. So how similar they are means how similar 2 to 3 is, how similar 4 to 5 is, how similar 6 to 8 is. So clearly, one criteria that we can see from here is how far they are from each other. So one very simple thing, if I say, it will be 2 minus 3. This is the distance of 1, this is the distance of 1, this is the distance of 2. So I'm going to say these are more similar as compared to 6 and 8. 2 and 3 is more similar as compared to 6 and 8. Now this difference that I am telling is not the only possibility, means there might be more possibility, and the data in itself, okay, because here I am talking about the data, okay, Xi and Xk. Okay, don't consider them as features. Instead, understand them as data, Xi, Xk. Okay, these are the two data, and every data is having only one feature, that is 2, 3, 4, 5, 6, 8. Now there might be a situation where every data is having multiple features. Okay, means right now, let's say this is only representing height. Okay, let's say right now it is representing height. Then again, there is some data that is representing the color as well of Xi. Okay, this is the data. Now here again for Xk, we have height right now. Then again, we can have one more data that is representing color. And as I already told you, this is C1, this is C2, this is C3. I cannot have C1, C2, C3. I have to represent it with numeric. Okay, some form, either RGB or the other color maps I can use, but I have to use this numeric representation. So in the same way, here we have a C5, C6, C7. Okay, I'm not writing because otherwise I have to write 3 RGB inputs. That's why I'm not writing. Okay, numeric values. So again, now you see, if someone asks you what's the distance between these two, Xi and Xk. Earlier, because you are having only one data, so you are directly telling 2 minus 3. But now you have C5 also. So altogether, you have to tell C5 minus C1, that is the color difference, and 2 minus 3, that is the height difference. But person is asking how similar Xi and Xk is. You are telling how similar two different features are of Xi and Xk. He's asking how separate Xi and Xk are, or how similar or dissimilar they are. So for that, I need one more approach or one more formula that can combine this difference. Means this C5, C1, this as well as this 2 and 3 difference, both can be combined, and very simple approach is there. The approach is Euclidean distance. I can use Euclidean distance, okay, to find out the similarity between two points. For example, let's say this is representing the color and this is representing the height. As we have started from earlier, this is the height, this is the color. Okay, right now it is only one dimension, the color. So, okay, you can assume this as gray. Okay, right now we can assume this as gray. If it is RGB, then obviously there are going to be 3 dimensions in the color itself. So here, beyond 3D, we cannot draw, but you can understand that everything is perpendicular to each other. And then here, if you see what we are trying to find out, we are trying to find out the different features average. Means 2 minus 3, that is one thing, the square of that, plus C, if I remember correctly, C1 minus C5, okay, means this is for the xi and this is for the xj, and then the whole square of that, and then under root of. So it is pretty much similar to like a distance between two points. Okay. It is sort of equation of a straight line only. Okay. It is going to give you the distance between the 2 points, the shortest distance between the 2 points, obviously. This is the equating distance that we can use to provide the similarity. Okay, this is the distance, or we can call it similarity, between the two different data points having multiple features. Right now, the number of features that we are having is 2. If it is 10, then also this is going to give you the solution. If it is 100, then also this is going to give you the solution. Another distance that we commonly use is the Manhattan distance, also known as city block distance. Okay, this type of distance is only used when there is some special restriction over the distance movement. For example, why it is called city blocks? Because let's say here you have city A, here you have city B, and you want to go from city A to city B, and in between there is a river. So you cannot obviously cross the river. If you have to go to city B, you have to take this path only. So that is the only possibility that you can take. Means only either horizontal or vertically. You have only 2 options to move, either horizontally or vertically. So this type of situation might be come in the traveling salesman problem or any other problem where you already know that you cannot have this type of short distances. You cannot take the shortest path. You are bound to use horizontal and vertical paths only. Then the Manhattan distance can also be used for the similarity and dissimilarity measurement. So now if you see, when the distance is large, the similarity measure is okay. When you have two things here, one is S, another one is D. Okay. Obviously, when similarity will be more, dissimilarity will be lesser. When dissimilarity will be more, similarity will be lesser. So they are obviously opposite of each other. So lesser distance means more similarity. Now, if you see this data point, here you have data point, and this is the 2 different examples of clustering. Here we have 3 clusters. Here again we have 3 clusters. Okay, but this is a better cluster. Why I'm calling it a better cluster? Because if you see, the compactness of the clusters, okay, inside of each other is better in this case. And in this case, the compactness is not better. This data point, for example, this data point, you can see, they look very far from these data points. In this data point, very far from this. So they are not compact. A good cluster is supposed to be very compact. In the same way here, if you say the data are very much distributed. Okay, so these type of bad clustering can be avoided if we use this similarity measurement in an effective way. So how can we do that? Let's see how that is possible. For that, we have 2 different parameters. One is known as intra-cluster cohesion, okay, or compactness. Okay, so that is basically used to measure the compactness of a cluster. Okay, so intra-cluster means inside the cluster, how close they are. So what we are going to do, we are going to use sum of square error. Okay, and that how we are going to use, first we have to define the centroid. Okay, centroid of a cluster, for example, if it is a circle, okay, the centroid will be the circle, this the center, this is the centroid. Now, obviously, even the shape is a little bit different. Then the centroid keep on moving, okay, because this is not a complete circle. Okay, this data point forming a circle. So obviously, centroid won't be the center, but it will be somewhere here. And how to define the centroid, that is also what we are going to discuss in a while. So what we are going to do, let's say this is the centroid right now, this is the centroid right now, this is the centroid. Okay. Centroid, you can say in very layman terms, it is the in-between point of all the data. Okay. So because this is a cluster, so this is in-between point. This is the cluster, this is in-between point. Okay. So this is the cluster, so somewhere here it will be. Why? Because this data is very far and these data are very closely to each other. But here we have more weightage, so that's why the centroid will be having a biasing towards this data, but it will definitely going to move away than this and towards this very distant data. Okay, that's why it is here. And now again, this type of centroid I'm going to use to measure the compactness, and the formula is very much simple because you have the centroid, the distance, this distance. Just take all the distance and see how close they are to the centroid. Ideally, what I want, this distance to be 0. Means all the data points are of the centroid itself, but practically it is not possible. So I will try to minimize this thing as much as possible. The lesser this sum of these squared errors will be, the better I'm able to compact the cluster. Okay. So this is the first inter-cluster cohesion, and the second is the inter-cluster separation. Means how far these two clusters are from each other. Means this is the centroid of this, this is the centroid of this. If the distance between these two should be as large as possible. Okay. Means for a good clustering, this should be as much compact as possible. This should be as compact as possible. And this distance between these two clusters should be as large as possible. Okay, so these are the points that we are going to use for further development of a good clustering algorithm. Okay, and again, if you see over the same data points, how many clusters are there? Okay. Or if a data is given, if a data set is given, okay, how many clusters one should form? For example, let's say a very typical example is you have is the movies. If you have the movies rating with you, okay, and you are supposed to form the clusters out of those movies, okay, on the basis of rating, on the basis of users review, on the basis of their different nature, means whether they are a romantic movie or they are action movie or they are horror movie. Okay, so these type of data you have, and you want to cluster the movies into different groups. Okay, so let's say in practice you have for example, you have IMDb data with you, 10,000 movies are there, and you're supposed to cluster. Okay, and you already have the features, different features with respect to every movie. Okay, because every movie you know in which year it is basically released, what is the average rating of the movie from the critics, from the users, and you have other features also with you. Everything is available, and you are supposed to cluster. But no one told you how many clusters you are supposed to make. So out of this 10,000, one can say, okay, I'm going to make 2 clusters. One will contain one type of movies. Now this type is very much subjective. Means one user might look the movies from only 2 aspects. Means whether they are action or they are not. Okay, so that is a cluster for that particular person. But other person might have more understanding. He might a fan of some hero. Okay, so he won't only interested in like action movie, but it must belong to a actor X. Okay, so that is that in that way there might be multiple clusters inside a cluster. So how many clusters one should make? That is also a question. And obviously, when you start doing this thing or start practicing this thing, sometimes we left it to the user to decide how many clusters one should find, one should look at. Sometimes we left it to the algorithms also to decide how many clusters will be appropriate. Okay, means if let's say you have, for example, okay, let me show you one example here. Let's say these are the data. These are the data. Let's say this is the data. Okay, so obviously if I give you the very first instinct here will be there should be two clusters, one this cluster, another this cluster. Okay, because they are quite separated from each other. So let the algorithm, sometimes we let the algorithm to decide how many clusters are optimal in this particular case. For in this case, two seems very good because they are quite having a quite good distance from each other. But one can say, no, I can see that there is a three cluster. This is my another cluster. This will be my another cluster. So there is nothing wrong or right in this type of clustering. Means if one say three clusters, that is also fine. Okay, depending on what basis and criteria one is making the clusters, that is totally acceptable. Okay, so that should not be. So now we are going to see one very famous algorithm, that is the k-mean clustering algorithm. Okay, and as you can see, it is proposed in 1967 only. So it is very like 50 years ago around it was proposed, and still it is used for many purposes, and it is a very basic algorithm from the clustering domain that have its own advantages. Okay, here you are supposed to, here we usually define how many clusters we want. Okay, until unless it is not a variation of the k-means, we define how many clusters we want. And why we are calling it k-means, here k basically represents how many clusters you want. So k is specified by the users. And so how we start the things. Okay, instead of going through the algorithm, let me show you the example directly. Let's say this is the setup. Okay, here we have two different features of every data point. Okay, if you see, this is my data point, this is my data point, this is my data point. So everywhere what I have is two features. For example, for this, the feature one is 4.1 something and feature two is like 0.9 something. Okay, so accordingly, I have a huge representation of data. So here you can see clearly. Now, what is C1, C2, and C3? This is basically the centroid, the C1, C2, C3. The question is, how do I know these are the centroid? I initialized it randomly. But the only thing I have to keep in mind when I'm doing this initialization, because the data have a limit, you can see it is never crossing 0, never exceeding 5. Similarly, here also never exceeding 5. So all the C1, C2, C3 should also be initialized within this limit, means 0 to 5. The farther they are, it will be better. Okay, for example, here they are quite distant from each other. So it will be good. Means why it is good? It is good for quick end of the algorithm. Okay, in a while you will understand why it's so. Okay, so these are my centroid. Now what is my objective? My objective is I'm going to measure the distance of this centroid from every data point. Okay, that is what I'm going to do. Now, this is one thing. Again, I have C2. For C2 also, I'm going to measure the distance from every data point. Okay, for C3 also, I'm going to measure the distance from every data point. Now, think from the point of view of the data. Okay. For data, there is a three possibility. For example, if you see from this data, it has three possibility. It can either go to C2, sorry, C1, C3, or C2. Means it can go to the cluster of C1, C2, and C3. The only thing that it have right now is the distance, okay, to decide where I should go. Okay, so the same way it is having two coordinates. Okay, the value is around 3 and 4 point something, so let's keep it 3 and 4. Okay, in the same way, C1 is having some coordinate, C2 is having some coordinate, C3 is having some coordinate. We are going to measure the distance between this, and this. Correct. Now, in the same way, for all the data points, the very same thing is there. They have three options: C1, C2, C3. So they are going to measure their distances from C1, C2, C3. Now, the closest centroid is going to be the winner. And here I'm going to use the strategy of winner takes all. Okay. And why the strategy winner takes all means C2 and C3 is not going to get anything out of this practice. They're only going to see this is going to now assign to this C. Okay. In the same way, the data that are closer to C2 going to be assigned to C2. Means every data is calculating and looking to which cluster I am closer to which centroid I am closer to, and it is going to join this. Okay. And after, in this way, one iteration will over. Okay, and as soon as one iteration will over, okay, these are the, you can say, data points. Means all these data points that you can see belongs to C1 now, because they are closer to C1 as compared to C2 and C3. In the same way, all these data points are closer to C2 as compared to C1 and C3. So that's why they belong to C2. In the same way here, for C3, all the data points are closer to C3 as compared to C1 and C2. So these data points now belong to C3. These data points belong to C1, and these data points belong to C2 on the basis of distance. Okay, very simple. Now the next thing is, because we have now new data points. Earlier, we initialized the C1 randomly. Okay? But now we have new data points with us. So what we are going to do, we are going to change this centroid also, because centroid is the mean. Okay? So what I'm going to do, I'm going to take and assume this is one cluster, and I'm going to take the mean of all the data points. How I'm going to take the mean? I'm going to choose the x coordinate, x coordinate, x coordinate, x coordinate of all the data divided by the number of data. So somewhere here I'm going to get. Similarly, if I'm going to do this thing, somewhere here I'm going to get. Similarly, if I'm going to do for this, somewhere here I'm going to get the mean. So that's why this algorithm name is k-mean, because with every run, what I am doing with every iteration, okay, here the mean is keep on changing. Mean the centroid kept on changing. Okay, this mean value, and k is the number of clusters. So 3 clusters we have initialized. So that's why this algorithm name is this. Now the very next thing is the movement. So here it is moving towards this side, this is moving towards this is moving towards this. Why? Because it is moving towards a denser region. Because I'm taking the mean. Whenever you are taking the mean, it means it is bound to move towards the denser side. Okay. So now doing so, again, if I use the very same approach, okay, once it moves, this is C1, this is C2, this is C3. Again, I am giving an opportunity to all the data points to recalculate their distances. Means this data point again going to calculate its distance from C1, C3, and C2, and see to which it is closer. Obviously, here we can, just by looking, we can see it is closer to C1. Okay, but for some data points, the situation might be different now, because centroid itself changed. For example, for this data, earlier it belongs to C2. It might possible that in a new scenario, it is closer to C3. So that's why I am giving a re-opportunity to all the data points to reconsider their situation. So again, they are going to reconsider, and you can see some data points will now move to new clusters out of C1, C2, C3, and accordingly, again, C3, C1, and C2 going to make a shift. And this shift and movement keep on happening till there is a settlement, means there is no more movement possible. This is the result of second iteration, C1, C2, C3. And you can see earlier this point, well, this point is now shifted into C3. Earlier it was belonging to C2, but it shifts to C3 because now it is closer to C3. Again, these are the new data points that we have. Again, we keep on running this process till there is no more shift of C1, C2 and C3. Once there is no more fix, means no new data is coming, no new data is going. Nothing is coming to C1, nothing is going to any other cluster. Nothing is coming, nothing is going, everything is settled. So that is my, okay. So that becomes my cluster C1, C2 and C3, and then I'm going to stop. Okay. Now here there are many situations. For example, what happens if instead of initializing C1, C2, C3 in this manner, I initialize C1, C2, C3 in this manner? Let's say C1. So what is going to happen? So in this case, obviously, the end result might change. So one can say, what type of algorithm is this where end results keep on changing? Because here we don't have any right answer. Nothing is right. Okay. So I cannot say the first result is better than the second result. Okay. So that's why it is definitely sensitive to the initialization of centroid. Okay, and there might be some variations in the result. Both the results are acceptable, and that's how a learning should work, because we are learning from ourselves. So if every time I'm going to learn the same thing, so it is not actually learning, it is something that is hardwired. Okay, learning is something where there is always a chance of improvement and there is a chance of change. Okay, because here what might happen that after successive runs, means after 100 number of runs, I might come up with a better clusters rather than with only single. So multiple times you try. So out of them, let's say 90 times, with 100 times, out of 90 times, the results are same. Okay, 10 times it is different. So obviously that 90 are more preferable. Okay, that is more better approach. Means you can say that are more robust clusters, you can say. Okay, and they're not sensitive to the initialization. So that is the benefit of this thing, having this random sort of nature or non-deterministic sort of output. Okay, so this is the thing. Now, if we talk about the backpropagation algorithm, if you remember the supervised learning, that is the error correction, where we already know what I'm supposed to get. Okay, and we used to target our equation in such a way that it trains and ultimately give me that. Okay, but here that is not the situation. Here the situation is altogether different. Okay, now obviously K-means clustering is a very old approach. Okay, now what we can do, we imply or we can apply this thing to the neural networks. Okay, also known as self-organizing maps. Okay, where we can use the very similar type of concepts. The winner takes all strategy. Okay, whichever node is closer, okay, that is going to be the winner, and I can make the clusters out of it. So I'm just going to show you one example of that as well. Okay. So these are the strength of K-means clustering. The strength is that it is very simple. Obviously, it is very old, so obviously it is very simple also. The time complexity, that is actually problematic thing also. TKN, so it in more number of data if you have, it is going to take much more time. The more number of clusters if you want to form, it is going to take more time. The more iterations you want to give, it is going to take much more. So that is problematic thing. We need something better, and we do have techniques that have a better time complexity as compared to k-means. But because of the simple nature, if you have like 1,000, 2,000, 5,000 data points, then k-means is best suited for that. If you have very bigger problem, then we have better. Okay. The problem is it is very sensitive to the outliers. Outliers means if in a cluster, outlier something like this. If there is an outlier in this cluster, then this type of formation will be there. If there is not that cluster, this outlier, then the cluster will be much better. So ideally, this should be the cluster, and the data must, or the algorithm must have the ability to recognize the outlier, but k-means don't have any such approach. So either I have to do it manually to find the outliers. Means by outlier, what I mean in terms of data, if you try to understand, everything is between 0 to 5. Let's say one data say 50. Everything is between 0 to 5 and one data say 100. So this data that is here somewhere on 100 and the data there is somewhere here 50, that is outlier. Because this is the only data that is telling like very absurd sort of feature as compared to the other data. So that I don't want in my data set because it is going to affect my cluster result in a very wrong manner. Okay. The shape of my complete cluster is going to be changed. So that's what we should keep in mind while doing this thing. Now let's talk about this competitive learning approach with the help of neural network. So here you can see, here we have 3 outputs, and it is a fully connected network. And here we have different features as we were having earlier also. In k-means used to have 0 to 5 range for this, all the features vector, one by one keep on coming. Here again 0 to 5, all the features vector keep on coming. So we can have in the same way multiple number of features. And here we have clusters O1, O2, and O3. So here what we are going to do in the very same way as we used in the earlier approach, okay, where the aim was to move the centroids with every iteration. Here, the aim will be to strengthen the bonds. Okay? Means if one time a data came and O1 wins, the next time when the data will come, again O1 is going to be the winner. So how I can ensure that? By strengthening the weights. Okay? So that's what we do in the case of neural networks. Okay. And here you can see a better example. Okay, let me show you the example. For example, if you see here, what we have done, we have started with this random weight. Okay, and with every iteration, just like in the case of k-means, with every iteration, we keep on changing the centroid. Here, we keep on changing the weights. If you see, the weights keep on updated, weights keep on updated, and here you can see almost this becomes 0, this becomes 0, this becomes 0, this becomes 0, this is 0.5, 1, 1, 0.5. So it is almost settled. Now from 50 to 100 there is no more change. Okay. So weights are almost settled down. The same way where centroid basically settles down. So this is the approach. If you have neural network, you can apply this approach over there. Okay, and the structure, if you see, this is the structure that I am going to get. This type of structure you're going to get. These are the 4 features that I'm inserting every time. And here we have 2 clusters. The minimum of D0, D1. The same way earlier we have the minimum distance. Here again, we have the minimum of these 2 are going to the winner. Which node is closer? Okay, which node is closer to this point. Let me give you one example. So that, for example, if you see here, you have the data. This is 1, 2, 3, 4 data. 4 data, 2 clusters we are supposed to form. This is the weight matrix right now that we have. Now you are going to find out whether this data is closer to this or is it closer to this. Okay, how? Simple, Euclidean distance. Just use that. Here we have Euclidean distance 1100 closer to this weight or closer to this weight. It is closer to this. So the closer is going to be the winner. So D2 is the winner. Okay. So because D2 is the winner, D2 is going to get the all. Okay. And because D2 is going to get the all, using this weight updation formula, I'm going to update the weights. Okay. And here the weight is getting updated for D2. For D1, there is nothing. It is the same way. The winners, the clusters, that is the winner. The centroid, that was the winner, going to take everything. Okay. So this is the approach. Using the neural network, you can apply the very similar thing. And here the possibility are more. If you have a huge number of data set available, then obviously we are going to use the neural network. Okay, so with this, I'm closing my talk. If you have any query, you can ask, please. Okay, I have one question. Yes, if you have any query, you can ask, please. I believe these questions are for the earlier presenters. Okay. Okay, if two data are at the same point, then what we can do in that scenario? See, if this is the situation, okay, if this is the situation, and if two data points are at the same location from C1 and C3, okay, then what we can do in this situation? Obviously, in that case, you can going to assign it to either of them randomly, okay, either to C1 or to C3. Okay, and if it is belonging to more than 2, then again you're going to do it on the random basis. That is the only possibility that you can do. And your objective is, just don't think your objective is that particular situation in that particular run. Okay, if you are doing something wrong. It means if you are assigning it to C3 and that is not very good. So don't worry. In the next run, it will correct itself. Okay, it will again go to C. Okay, because everything is moving. So that's not a big problem. Because it is going to settle down after around, you can say, 100 number of iterations. It is not like in 1-2 iteration everything is going to be settled down. Okay, so in case of equal distance, that you can do. Apart from K means, yeah, apart from K means the neural network approach that I told you, that is the approach where you should look into for the data clustering, because these days what happened that the data size are usually very large. Okay, and in that case, the algorithms and the data points and this SOM approach, self-organizing map. Okay, so this approach you should definitely look into. Self-organizing map. I have given you the basic intro of self-organizing map. We haven't touched everything because time was limited. Maybe in the practical sessions they will tell you more about this testing and training phase of self-organizing maps. And definitely it can be used to like multiple areas. Okay, whether you are doing the things in the communication domains, whether it is a clustering of sensors, let's say sensor area networks are there, or you are doing in signal processing, everywhere it can be used. Okay, wherever you have to make a bunch, okay, clustering you're going to use. Yeah, if anybody else have any question. Wait. Okay, I believe there is no more queries. E&ICT, if well,
yes, sir.
listen. Yeah.
So
What should I do?
participants, you can just drop your queries in the chat box. It's open, and also in the Q&A section.
Okay, I got 2 queries. I already answered. I guess there is no more query. Already answered. If you have, yeah, definitely you can ask.
Sir, there is a query from Sakshi Anand. Can we use clustering for temporal data classification?
Can we use clustering for?
Temporal data classification?
No, no, no. Clustering is not for classification. Classification is supervised learning. Clustering is unsupervised learning. Okay. Whenever you're talking about the classification, you have to use supervised learning. So for supervised, there are many approaches. Obviously, SVM is there, ANN is there. So many approaches are there. Okay, so you have to use that. Is there any need to have a cluster head? Cluster. I didn't get that question. Cluster head means? I didn't get the question. Can you clarify this thing? What you are asking?
Rangarajan sir, you can type your query in the chat box also.
To have minimum distance from other point. No, there is no such criteria like there has to be a means how far two different clusters could be. Means I believe you are asking for the centroid. Okay, the distance between two centroids. So no, there is no like fixed rule. As I already told you, this is an unsupervised learning. Okay, and in unsupervised learning, you have to make your own rule. Okay, so that's why there is no fixed thing. Okay. When you are going to run the thing, okay, in some cases even the distance might be in decimals like 0.5. In some cases even 100 is not sufficient. Okay, so that totally depends on what type of data you are going to provide. So you cannot make rules without the data. So first we look at the data, then we form the rule. Okay, and obviously we are not going to form, the algorithm is going to form. That is the thing.
Sir, there is one more question.
Okay.
If we want to do prediction from a set of data, can we use clustering?
If we want to use prediction,
yes,
no. Sir. Prediction is again doesn't come under the clustering thing. Yeah, if you want to predict on the basis of clusters, for example, if you want to create a recommendation system, means let's say there are people have a same sort of taste, and you want to predict or recommend, if the prediction in that sense you're talking about the prediction world, you want to predict what type of restaurant people might be interested in, or what type of movie people might be interested in. If those type of prediction you want to make, then definitely the clustering is the best approach. Even many of the systems, for example, the websites that we used to purchase from, they use the recommendation system to recommend what type of product we might be interested in based on our own previous history of search, as well as from the geographical locations users which have the similar type of taste, age, gender. Okay, so these type of data they keep on collecting so that they can recommend better and better product, so that they can increase the sell. So in that sense, if you're talking about the prediction, then definitely yes, clustering is the only approach that we are using. We are making different clusters of users, and then we are using them for increasing our sales, obviously. That's what we are doing. Okay. Anything else? If you have any other query?
Sir, there is one more question. In k-means clustering, do we need to initially assume the centroid value?
Yeah, definitely. You have to assume the centroid value. Means assume means we are doing it randomly. Okay. And there are many other approaches where we can initialize those centroid using a specific approach. That is also possible. Okay. But if you have very like 1,000, 2,000 number of data sets, you can do it randomly. No problem. It will do the job for you. Okay. Yes. Anything else if you have?
Sir, there is one more query. How to choose k value for any problem in k-means clustering?
How to choose k value
for any problem?
Yeah. That depends on the problem. Okay, and that depends on the user. As I already gave you one example, in the case of, for example, the movie clustering. Okay, one can have a situation where he or she is only interested in two clusters. Okay, one is the action movies and another one is non-action movies. So in that case, k value is going to be 2. Okay, because I'm interested only in two clusters. Either the movie is action or it is not action. Another possibility is I'm interested in action movie. Along with that, the movie must belong to Mr. X. Then action movie belong to Mr. Y. Or the action movies must have IMDb rating of 8 or higher. Okay. So in that sense, the clustering is very subjective, like depending upon where I'm doing it. So k value is not fixed. Depending how many clusters I want out of that data, I have to define what should be the optimal value of k for that particular problem. When the problem changes, the value of k is also going to change.
Dear participants, we have shared our email ID. In case you have any other queries, you can write to us in our email ID given here. So that's all from the side of participants till now, sir.
Okay. Okay, so thank you very much for having me. Should I close then?
Yes, thank you, sir. Now you can disconnect.
Yeah, thank you. Thank you. Thank you very much.
Now we are moving towards the hands-on session. It is continuation of the hands-on, which we have done in part 1. It will be taken by Dr. Ridim Grover, ma'am. Ridim, ma'am, I'm making you the presenter.
Yes, I am in a panel. I think I'm in the panel already.
Yes, ma'am.
Oh, you have to make me the presenter. Okay.
Yes,
So I'll start sharing my R window. I'm assuming that all the participants are same who were there yesterday
ma'am.
also. Yes.
All participants are same.
Okay. So I'll continue with the introduction to R section. We covered quite a bit of things yesterday, which were how to create vectors, how to create matrices, and how to load data sets, how to use like number of rows, particular number of rows and columns in a matrix, like indexing the matrices and the vectors. And I think lastly, we also covered some of the graphics like scatter plots and contour plots and image plots and three-dimensional plots also. So I'll end this introduction to R section first, and basically we'll just see some of the functions to again plot the data set that we loaded yesterday. So I'll just share my screen. I hope every one of you have your R Studio open. And what we can do is we can just start from the data set that we loaded yesterday. So everything is clear for now, like there is no object in the environment and there's nothing in the console, and I've opened an untitled document, although I do have all the codes here in the introduction to R. I'll just type in with you so that we can do it together and I can pace myself. So what we'll do is we'll just use the command that we learned yesterday for loading the dataset auto. So what we did was we did use the command read.table, right? And we have our data set auto.data, and we read this into an object called auto, which is actually a data frame. One more thing that we did was we had specified that the variables that are present in the auto.data are to be, we have to tell R that these are the variable names and not the data itself, so that the variable names do not appear in the first row. So we mentioned that header is true, right? And let's see what happens. So yes, we have the auto data set with 397 observations and 9 variables. And if we want to view the data set, we can use the view function and view the data, which gives you the data set in the spreadsheet format. And if you can see here, the data set starts from the first row and the variable names are mentioned above that as a header. Okay, but the problem with this data set was that there were some missing values here, which are actually represented by question marks. So what we did in this read.table command, while reading the data itself, we specified that any strings which are question marks are to be treated as missing values. right? So NA.strings basically tells R that anytime it particularly sees this character, this question mark, it should be treated as a missing value of the data matrix, auto. We also gave an argument called strings as factors. And we told that this is true, which basically is telling R that any variable containing character strings should be interpreted as qualitative variable rather than a quantitative variable. Because if you don't tell R that, it will always treat it as a quantitative variable. So this is how we read the dataset auto. Lastly, before going into more analysis of this data, what we also did was that we treated the missing values by deleting them, because we saw that there were only 5 rows with the question marks with the missing values. So what we do is we use the function na.omit for the data auto. Oh, I by mistake printed it. So what you should do is you update your auto data frame with this function na.omit. So now the new revised dataset auto will contain 392 observations of 9 variables. If you can't see in the environment variable, you can use the dimension function also to check that. So basically what you have done is deleted the rows with the question mark with the NA values, and it basically shows you that 5 number of rows had missing values, because originally it was 397 cross 9 and now it's 392 cross 9. Okay, so this is what we had yesterday also. I think the last command that we used was this names command to see what are the names of the variables in the auto data set. And this is it. So now let's look at the plot function, which we also discussed yesterday in one of the basic commands that we learned in the beginning. Now we use this plot function to plot the first 2 variables in the auto data set, let's say MPG and cylinders. So what we do is we, on the horizontal axis, I want to plot cylinders. And on the vertical axis, my response variable is MPG. So now it gives me an error that object cylinders is not found, of course, because we didn't mention that R has to look for these objects in the auto data set. It says that it has not found these variables. So to specify where these variables are, what you should do is basically mention the name of the data that you want. So you again go back, press the up arrow, and you can get back to the previous command. But now instead of typing cylinders, what you will type is the name of your data frame from where you want to pick up the variable, followed by the $sign, and then you mention the variable name cylinders. Right? Similarly, here also with MPG, the variable is in the data frame auto. So auto $MPG will give you the variable MPG. And now if you use this command, you can see that in the plot section on the right hand side, you get a scatter plot. Now, a way around this using this $sign, if you don't want to do that, what you can do is also use a function called attach and pass the data frame auto to this function as an argument. Okay, and this function will basically tell R that it has to make the variables available by the name itself. So if you press, if you enter this command, attach auto, and now you don't need to specify basically this, that the cylinder and MPG are variables of auto data frame. R can access these variables directly. So you can use the command which we originally used, plot cylinders, MPG, comma MPG. And you can see on the right hand side, you again get the same plot. Okay, so either of two will work. Now you can see in the plot that R is treating cylinder as a quantitative variable because it is basically a numeric data. So if you see in the view view part of the auto data set, the second variable here, cylinders, it takes numeric values, right? You see 8, 4, 6, 8. It is also quite visible that what kind of value cylinder takes. So it's ranging from 3 to 8 at a distance of 1, except for 7, right? So it basically takes a very few discrete values, and what we can do is we can treat this as a quantitative variable rather than a, qualitative variable rather than a quantitative variable. And to tell R that it's a quantitative variable, we use the function as dot factor. So what we do is we tell R that cylinders is to be treated as a function which is a qualitative variable. So we use the function as dot factor for that, and we pass this. So we don't have to write auto dollar cylinders here. We can just write cylinders because R knows that this has to be this variable is present. It has attached this to the environment. Okay. So now R will treat the cylinders as a qualitative variable, and how you can check that is that now if you plot between cylinders and MPG, now instead of the scatter plot, R will give you a box plot. So basically at each value that the cylinder takes, you get a one-dimensional plot, a box plot for the Y values, which is basically your MPG data. Right? So I'm assuming that everybody is familiar with a box plot, but just in case, a box plot is basically to depict that. So basically you have a median value, you have quartiles, and you have range of the data. And if any value lies outside the range of the outside this interquartile range, then it will plot it as separately as an outlier. So usually the dots that you can see, the data points that are beyond these whiskers, they are called. So beyond these whiskers, whatever data points are there, these are usually treated as outliers in the data. And these, it is basically very easy to construct these box plots. So if in case you don't know and you would like to know how the box plot is created, you can let me know. Otherwise, I'll just go ahead. Okay. So now with this plot function, since cylinder is a qualitative variable now, we have the box plot on the right hand side for each of the values of the cylinder takes. And you can again use different options and customize your plots. For example, you can use in the same command in the plot function, you can use another argument called color. And it will color your box plots to red. You can specify any color you want. Similarly, there is another option, var width. So I'm just using there are a number of arguments that you can use the help file and check it out that what kind of options are available and how you can modify. So you have to play around with the function and different arguments and give them different values. So this is something that I would do. So I'm changing a few of the options. So var width will basically reduce the width of the boxes. according to the standard error. So you can read about this plot function in the help file and see what kind of arguments are there. I think we discussed this yesterday also. So any of the arguments that you want to check, you can check. Actually, a better way to check for the box plots will be that you go into the box plot function and check what kind of arguments are given there. Here, since we told R that it is a qualitative variable, it automatically produces the box plots. But in case it doesn't, you can also go to the box plot function instead of the plot function and plot that. So here, there are again a number of options to choose from. So this is the bandwidth option that we chose. And what it does is it, if you give bandwidth as true, although the default option is false, the boxes in the box plots are drawn with widths proportional to the square roots of the number of observations in the groups. Okay, another option that you can give, since there are a number of box plots there, you go back to the plot command and you can set horizontal option to true. So that will basically tell R to plot the box plots horizontally rather than vertically. Vertically is the default option. I'll just put my console here so that it's more visible, the commands that we have used. Okay, so now there is another function for plots. We'll consider we'll just see how to plot histograms since we're talking about one-dimensional plots, box plots. We can also plot a histogram, let's say of MPG variable, like this. And again, there are many options that you can give here. For example, you can specify the color. So color, you can say that choose color 2, which basically gives this red color. You can also write the name of the color. So it's a different shade of red, but yeah, you can use numbers or color names. So there are various colors and color names that are options that are available, and you can choose any one of them that you like. Similarly, what an important thing to choose while giving the parameters to a histogram can be the number of breaks, so the number of bins. So basically, let's say I want to have 15 bins in this histogram, which will give me a better representation. However, you should be really careful about doing this, because too many bins and too few bins both can distort the histogram representation. So you have to be careful while choosing the number of bins. But there is an option here. So there are specified rules for choosing the bins, so you can go through them and choose accordingly. And R gives you the option of specifying the bins and getting the plot that you desire. Okay, so there is another function called pairs that will create a scatter plot matrix instead of the scatter plot between the two variables, since auto dataset has 9 variables. And if you want to see scatter plot between all the pairs of variables in this auto dataset, what you can use is the pairs function and pass the argument of the auto dataset. And you can see that on the right, since the plot window is very small, it's not a very beautiful picture. Maybe you can zoom it and just check how it looks like. So there are a lot of combinations because there are 9 variables. So for each variable, you will see it's a 9x9 matrix, scatter plot matrix, and for each variable, it will create this scatter plot. For each pair of the variable, I'm sorry, it will create a scatter plot, right? Now you can also use this function to create scatter plots for subset of variables. Maybe you don't want to create a scatter plot for all the variables present, since it was not very visible what is happening there. You can choose a few number of variables and plot scatter plots for them only. So what you will do for that is that you mention okay, this is the command. So you use this pairs function, and in the pairs function, you pass the argument like this. So you have a twiddle here, followed by the variables that you want. So let's say I want the MPG variable. Then before adding the next variable, you use this addition sign. And you want a displacement variable. See, R already knows the variable names, and that is why it is giving you that option. So you can just press tab as soon as it recognizes it. Then you have horsepower. So you can check the variable names in the auto function, in the auto data set by pressing the names, using the names function. You have weight, so that is what you want. And you want maybe, let's say, acceleration. You also have to specify the data set. So data auto. So this is how the pair function works if you want to just select a few variables from the data set. So now you can see the plot. It has fewer number of rows and columns because we have given only 5 variables out of the 9. And that is how it looks like, right? So between any two variables like MPG and displacement, you have the scatter plot here and here. Okay. If anything is not clear, or would you, if you want me to repeat anything, otherwise I'll just proceed ahead. Okay, another important function before we go ahead with lab on linear regression, summary function. So using this summary function, you can summarize any data set. And let's say I want to summarize my auto data set, because that's the data set we are using currently. So we press, we enter auto as an argument on this in the summary function, and this is what we get. So you can see for each of the variables present in auto data set, like MPG cylinders, displacement, horsepower, what it will do is it will summarize in this form. It will give you the minimum value of the variable that the variable takes, the maximum value that the variable takes, the median, the mean, the first quartile, and the third quartile. Similarly, that it's doing that for each of the data sets, right? I'm sorry, I don't mean each of the data sets. What I mean is each of the variables present in this data set. And the last variable, you can see it's a name variable. So it's a qualitative variable. So R will just list the number of observations that fall in each category. So these are the categories of this variable name, and maybe five observations have the name AMC Matador, and other five observations have Ford Pinto, and so on. So this is what happened when you summarized auto data set altogether. So it summarized every variable of the auto data set, and you can do it individually also. Suppose you want to just summarize one of the variables. So you use the same function summary and pass the argument MPG, let's say. So it will just summarize the first variable and give you the same statistical characteristics, that is minimum value, maximum value, quartiles, and median and mean. Okay. So another thing that I would like to tell you before doing the lab section on linear regression, which is what we're going to do next, just to see that how to quit R and how to save the workspace. And if you want, you can even save the history of commands that you have used, so that whenever you come back, you can load the history and run the same commands if you want. So what you do is to, if you have finished using R, which we have not, so we'll just start it again. So what you do is you press the function Q, which stands for quitting. So it will just tell R to shut it down. And if you press this, it will give you an option of saving the workspace image. So basically, if you press yes, it will create a .r data file, and it will save your workspace there in your working directory. So let's just say I want to save it. So I'll just press yes, Y, and enter. And it will quit R. But now I want to go back to it. So I'll just restart my RStudio and share the file again with you. So another thing that you can do is you can save history. I'll just tell you how, but we'll not exit the exit R again to see, but let's just see what are the functions that are used for that. So save history basically saves your history into a file. And I did it before, so probably you'll find a .r history file here. So this is what it looks like. Similarly, when you restart R, what you can do is you use the function load history, and it will reload all the commands that you have performed before. So these are some earlier coding commands, and that is what it is showing. Yeah. So you have to be in the same working directory where you were doing. So for example, I'm not in the same directory as yesterday. So I'll just go to that directory. This is that. And set it again as a working directory, which we learned how to do yesterday. Just a quick recap. And now since we are in the working directory, if I go to history, I'll have to load history. So I can just clear this one. And you can see that I get the same commands that I used today. Right? Okay. So maybe we can take 2-3 minutes to just see if anybody has any doubts, and then we'll start the section at in just 2-3 minutes about the lab on linear regression. So I see a raised hand. Do you have a question? Harshavardhan Ahire.
Hello. Good evening, ma'am.
Hello. Good evening.
Yeah, ma'am. Yesterday, what session you have taken? I actually installed RStudio very late, so I could not practice along with you. So could you please show us how the CSV file is read and then how it is converted into .data file?
Into that data file. So we don't have to convert it into that data file. What we can just do is read the CSV file and use that file to do everything that we did today.
Okay,
so I can show you
what is
how
the
to.
instruction for the reading CSV?
Yeah, so
I
as we
tried
used.
read.csv, but it didn't work out. And we don't have the
Okay.
yesterday's video also, so it's not possible for us to recollect the things.
Oh, is it so? It's not very clear in the video?
No, we don't have the video yet.
Oh,
It
you
is
don't
not
have
yet
the video.
uploaded.
Okay. Okay. So I can just show you how to use a read.csv file. And yeah, later on you can check the video out also in case of any confusion. But yeah, we'll just see how to use it quickly.
Madam, the video has been shared live, so participants can directly find our videos in the YouTube. We have shared the
Okay.
details in our Google Drive.
Okay, so did you hear that?
Yes, ma'am.
Okay,
I
so
heard
yeah.
it was not yet uploaded. I said that in that way, as I could have practiced in the live.
It is live. It is live.
So I
We
will
need
practice today, and if I have any doubt, then I'll clear it
Sure,
up.
no problem.
Email you.
It's just a small command. Anyway, I'll show you that. And yeah,
Yeah.
later on you can definitely practice from the video also. And I'll share the codes also, so then you can just check from there. So
That would be very nice.
Yeah, definitely. These are actually all open source codes and they are readily available. So I'll share the link of the book and the code, and you can directly look and even go further. So the is that you have to practice a lot. Okay.
Yeah.
So the read.c, can you see my RStudio screen?
Yes, ma'am.
Okay. So this is what I'm doing. I have my data file here in my environment, auto.csv. Right? So you have it open in your environment also in the file section.
Okay.
It should be just available in your working directory. Otherwise, you have to specify the address. That is also fine. So what you do is you use this read.csv function. And since I don't need to go anywhere, my working directory is the one where the data set is available. What I'll use is read.csv function and enter the file name. So auto.csv is my file name. So the first command that I did today was read.table with the same argument auto.data instead of auto.csv. But it's the same command, just that you are using read.csv function instead of read.data function, and you pass the similar arguments like header is true.
Yes, ma'am.
Yeah. So you run this. Okay, it's not running. So error in read.table file header. Okay. Yeah, it's running. So I think instead of true, what I had to give is just the T command, or true should be in capital letters, and then it will run. And what you can do is just save this into the auto object maybe auto to object, and just check how it works. So yes, so now you can go to your environment.
Yes, ma'am,
These are
I've done
some,
that.
and you can even just use the view function to view it as a spreadsheet. And it will topple the file actually. So I hope it worked for you also.
Yes, ma'am, I'm working on it.
Sure. So in case anybody else has any questions regarding today's or yesterday's commands and they could not do it, because it will be easier for you and easier for me also to proceed further in a good pace if we are clear with the commands that we have discussed so far. And it makes it more interactive also. Otherwise, it's like I'm speaking to a wall. So even a little doubt is
Thank you
fine.
very much, ma'am. My doubt is clear. Thank you very much.
Okay, perfect. So it's working, right?
Yes, ma'am.
Okay, good. Okay, so maybe we can just continue with the next section, where we will basically learn how to fit a linear regression model. We'll start with a simple one and we'll proceed to do multiple linear regression also. And I think that's what we will be able to cover today. So I'll just again, yeah. So I'll clear my console and my environment also. I don't think I need any variables. Let's just start from the beginning. Go to the plots because I want to make some plots and those should be visible. Okay, so what we work with is a particular library which is available in R. So this library is called MASS, M-A-S-S. So to invoke any library in R, what you do is you use this function library and you enter the library name. So why I'm loading this library MASS is that basically it has a lot of data sets. It's a huge collection of data sets and some functions also that can be used for linear regression very easily. So some of the functions are directly available in R, but some of them are in set libraries, and to use them, you have to invoke those libraries. So for me, it just shows a warning message that MASS was built. It does not matter. I can still use it. The only problem is that some of you can get the error that the library is not there. And in case that happens, what you have to do is you'll have to install the package. So there is a command called install.packages. And you mention the name of the library that you want to install it for you. So I'll not run this command, but this is just to tell you that how you, just in case you are getting the error that the library is MASS is not there, you can run this install.packages and download the library. So another library that we are going to use today is called ISLR2. So it stands for Introduction to Statistical Learning, 2nd edition. So again, it's a book that I'm following for these lab sessions as well as I used it for my lectures. So it's a great book on anyone who wants to start learning about statistics and statistical learning techniques from the scratch and go deep into it. They can refer to this book. It's both theoretical and practical. So it will help you both ways. So, okay, again, for me, it's a warning message, but I have both the libraries there installed with me. I'm hoping now you have also installed it. Okay, so the data set that we are going to use is called a Boston data set. So this is the name of the data set, and it is in the ISLR2 package library. So it has to be, the library has to be invoked before talking about the data set. So what you can do is you can just check that the what does this data set entail, Boston. So I'll use my help file, and it will work only if you have installed this library. So now it's giving you two options. So there is one Boston data in the mass package that we invoked, and the other is in ISLR2. And what I want to invoke is this one. So let's just go to this. So here you will find a good description of the data set. So it's basically a data set containing housing values in 506 suburbs of Boston. And to use it, you just have to use the name Boston as a function. And it contains 13 variables. So these are the variables. You can also print the variables using the function names that we learned yesterday. But using only this will basically give you the names which are short forms of some of the shorthands used for some of the long sentences that you can find here. So invoking the help file will be useful so that you can exactly know that CRIM basically stands for per capita crime rate by town. Similarly, ZN stands for proportion of residential land zoned for lots over 2,500 square feet, and so on. So you have all the variables and their interpretations here. Okay. To see how the dataset looks like, I'll not view the entire one, but I'll use the head function to see the few rows of Boston dataset, how the data looks like. And this is how it is. So it prints all the variables, but it will print only the first few rows. So in this case, it's printing first 6 rows. So now what we'll do is we want to fit the linear regression line, but maybe what we can do also before fitting the line, we'll just fit a simple linear regression model. So choose any 2 variables. So our y variable is basically this this variable, MEDV, which stands for, here you can see, so it's the median value of owner occupied homes in $1,000. So this is our response variable, and the other 12 predictors are the other variables at LSTAT, PT ratio, tax, index of accessibility to radial highways, and so on. So what we want to do is we want to predict or explain the median house value using these 12 predictors. So first, what I want to do is I'll just explain this median values using LSTAT variable, LSTAT predictor. So I would like to just see how the scatter plot looks like between these 2 variables. So we'll use our plot function and plot a scatter plot. Okay, so yeah, of course it will give me an error because we have not told where to look for these variables. So just use the function attach. And now R knows where the variable names are. So you can use plot or just press the up arrow twice and you get the same command. And you can see that the scatter plot between these 2 variables here. Okay, obviously I did a mistake here. What I should have plotted is LSTAT, comma, the median value houses, because that is what my response variable is. So plot command always works in a sequence. You have not specified that what is x and what is y. So it will treat the first variable as x, which it will plot in the on the horizontal axis, and on the y axis it will plot the second variable, the response variable. So this is what the command should be like. Now it's fine, right? Okay. Now to fit a simple linear regression model, what we do is, so we are fitting the linear regression model between these two variables, treating median value as the response and LSTAT as the predictor. So you use the LM function for that. And LM function, the syntax for that is that you, I'm just telling you the syntax, so don't enter this command. What you are doing is you use the LM function, and the first argument is that you tell the response variable. You use the twiddle symbol, and then you mention the predictor variable. Okay, and just that won't do. So basically what you also have to tell, or it might work actually, because we have already done the attach argument. So it knows the variable name. So instead of y, I'll just enter my median value of the houses, and instead of x, I'll use this LSTAT variable and just see if it works. So I don't want it to print everything. So what I'll do is I'll just assign this object lm.fit and store my linear model, whatever it will do. We'll see what it does to this object. Okay. Now I want to see that what exactly happened in LM by passing the LM function. So I'll just see lm.fit, what it gives. And this is what it tells. So basically it will give you the information about the model, about this, about the formula of the model that it has fit. So it has used this median value as a response variable, and it'll start as a predictor, which we passed as the argument also. And it will give you the coefficients that it has used to fit the model. So there's an intercept term. It's a simple linear regression model. And there is a slope term. So we are mainly interested in the slope, although obviously both are important. So there's an intercept and the slope, and this is what your linear model function will do. So it will fit the regression line with the with these parameters. So if you want more details about this, what you can do is use the summary function that we used a little while ago. So you use the summary function on this object lm.fit, and you get more information about the fitting. So much more information. So you have the formula again, and now you also have information about the residuals. So we know that the residuals are basically the difference between your observed data and your predicted data or the estimated data. So there is, it is summarizing your residuals basically with these statistics. And then what you have are the coefficients that it has estimated. So you have an intercept term and the slope term, slope for the L corresponding to the LSTAT variable, because that is a variable that we have used to explain our median value of the houses. And these are the estimates. Along with the estimates, which was the information that you were given here also in the lm.fit function. Now you have much more information in the sense that you also have the corresponding standard errors, which is the square root of the variances of these estimators. And then you also have t values and p values. So t value in this context is basically what it is doing is, I am not sure whether you are aware of it or not, but it is doing a hypothesis testing. So we discussed hypothesis testing yesterday, that we start with the default theory, H0, a null hypothesis, and depending on the data, we see whether to accept or reject the null hypothesis. So this t value is basically something, is a statistic which is calculated on the basis of the data, and it is used to accept or reject the null hypothesis. And in the context of linear regression, usually our null hypothesis is that there is no relationship between the two variables. So once you have done the linear model fitting, what you want to do is you want to check whether there is actually a relationship between y and x or not. Like, give you, if you give any two variables y and x and use this LM function, it will give you a linear fit between the two variables. But you need to check whether the linear fit is appropriate or not, right? So one way to do that is go for the hypothesis testing, where you hypothesize that there is no relationship, which is your H0. And based on this, your data observed, you calculate this t value, t statistic. Based on this t statistic, you correspondingly also calculate this t value, which is basically your probability of observing an extreme value as extreme as the t value. And the rule of thumb is that if this probability is very small, then you can reject the null hypothesis. Otherwise, you do not have enough evidence to reject the null hypothesis. So we definitely cannot go through the entire theory. I'm assuming that you know about this. If not, you will probably cover these things later on in other lectures in FTP, and also you can go through this book to know more details on this. But this is the basic idea. This t value and p value is just to evaluate whether these are significant variables or not, whether L stat is actually a variable which has significant effect on the response, this median value variable. And in this case, since your p values are really small, almost negligible, it means that they have a significant effect. So you cannot, so you do reject the null hypothesis that there is no relationships, and you conclude that there is a relationship between L stat and median value. Now, the other information that you get from this summary function are this residual standard error, which is basically your square root of the variance of this error random variables, error estimates. Then you have R squared function and adjusted R squared function. These are again your measures for assessing how good the fit is. So a good R square value is basically R square basically lies between 0 and 1, and a value which will be close to 1 will basically represent a good fit, a very good fit. So this is an okay fit. Similarly, you have adjusted R square, which is an improvement over the measure R squared. Again, you have to read it theoretically, how it works. So it's an improvement in the sense that R square has this limitation that if we keep on adding variables in a multiple linear regression model, R square keeps getting better and better. So you do not know where to stop. So adjusted R square basically takes care of that, and it incorporates a number of variables also in the formula, and therefore it gives you a criterion of where to stop adding the variables in the model, because you cannot keep on adding the variables even if your fit is becoming better and better, because that will lead to overfitting. Right. Similarly, your F statistic is another measure to see whether your model fitting is good or not, and a value which is far away from 1 for the F statistic is a good representation, is a good sign. It will show that you have fitted the model fitting is good. Okay, so this is how the lm.fit can be summarized. Again, it will be great if you can go through the theory once, you'll understand this better. The summary function basically gives you a lot about the linear model fitting. If you want to know what other things are available in this lm.fit, because just typing lm.fit gives you the formula and the coefficients only, but there is much more to it. So what you can do is you can use the function names on lm.fit. And this is all that it does. So it has coefficients, residuals, effects, rank, fitted values, and whatnot. Right. So now here you can go to the coefficient function. So there, one way is to go to the use the coefficient function to find the coefficient values that the linear model has used. The other way is that you can use this also. So in lm.fit, you have all these variables, and to access them, what you can do is, again, as we did for the data frame, you enter the name of the data frame that you want to enter, and then you follow it up by a $sign, and these are the names of the variables that are there. So you can use coefficients to know what are the coefficients that the model has used. And check this. So you get the same result. Now, another thing that you can do is find the confidence intervals. So how you find the confidence intervals is by using this function called confit. And you pass the argument lm.fit. And what it will do is it will give you a confidence interval for both the parameters, both the parameter intercept as well as your slope parameter corresponding to the LSTAT variable. And by default, it gives you a 95% confidence interval. So 2.5% on the left tail and 97.5 on the right tail. There is another way to find the confidence interval, and using that function, you can also find a prediction interval. So there's a function called predict. And what you can do is you can pass the lm.fit function to it, where we were fitting a linear model between that median value and LSTAT variable. And you also mention what are the values of LSTAT at which you want to predict the median value of houses, because prediction means you are considering those test cases which are not already there in the LSTAT variable, right? So you will just mention that. So to mention those values, what you do is you create a data frame of LSTAT function. And maybe you want to evaluate the value of median value houses at LSTAT equal to 5, 10, and let's say 15. So at 3 values of LSTAT, you want to evaluate, you want to predict your response. And along with the prediction, you also want the confidence interval. Right? So what you will, there's another argument that you can pass in this function called interval. And you can mention which kind of interval you want. So there are two kinds of interval that you can invoke here. One is the confidence interval and the other one is the prediction interval. So if you use the confidence argument, you get the confidence interval, of course. So the first column basically corresponds to the predicted value. So at LSTAT equal to 5, your prediction for the response median value of the houses is this, 29.8. Similarly, at LSTAT equal to 10, it's 25.05335, and for 15, it is this value. And you can see that these confidence intervals, basically the second column represents the lower limit of the confidence interval, and the upper value of the confidence interval is represented by the third column. And you'll see that obviously these values will lie between your confidence lower and upper limit. So instead of the confidence interval, if you want a prediction interval is basically an interval at a particular value of L stat rather than the average value. So you can mention that. The prediction intervals are a bit wider than the confidence intervals because they are not averaging out the irreducible errors. So this is how they look like. Again, they are formed around the same values, which are the predicted values, but the band is different. The confidence band and prediction band are different in the sense that the prediction intervals are much more wider. Okay, so this is what we, these are the functions that we can use to summarize our fitting, but we have so far not actually seen what the fitting looks like. So let's do that. So we'll use the plot function. And our x-axis, we want to plot L stat. And on the y-axis, we want to plot the median value. And actually this plot was already there. So just in case, we just plotted it again. So this is what your scatter plot looks like. And to this, you want to add the line that you have fitted using the function lm. What we'll do here is function a. So AB line is a function that can be used to plot any line with a given slope and intercept in this particular plot. So the whatever plot you have plotted just before the using the function AB line, it will plot the line in this plot. So for now, I want to plot the line that the linear model fit has provided. So what I'll do is I'll pass the argument lm.fit. So if you see here, it's not a very good plot, but if I zoom it, you can see that it has plotted the line on the same plot, right, on the scatter plot. So this is the line that linear model of the fitted linear model that we found out using the lm function. Oh, okay, somehow I stopped the entire thing. So just in case if I'm going too fast or if you have any questions, I'll just share my RStudio window again. Okay. So now we have used this AB line function to show how the fitting looks like. It's not a very great fitting, but it's an average fitting, which is also very clear from our R square value here. Okay. Another thing that you can do is, since this line is not very visible, you can again use several options in the AB line function and choose what you want it to look like. So basically what I'll do is I'll just change the width of the line first. So LWD option is to change the width of the line, and I'll set it to, let's say, 3. So it's a much thicker line now. So better visibility is there, and you can zoom it and see that it's much more visible. Right? Now, another thing that you can do is you can change the color as before. So you mentioned, and let's say again, right? Much more visible. So again, to learn these your plot view, to if you want to work to explore more and more that are available in our help file and explore. you can do, I'll just mention quickly, is you can use this function argument, actually, not the, this is PCH. What it will do is vector or that R is currently using circles to plot the scatter plot. What you can change this to, let's say, plus sign. Oh, so I use what I wanted to do is change. So I'll go to my scatter and how you can change that. So basically what it does is it circles with plus signs. So it is also useful when you're things together and you want to distinguish and use different characters or variables. Same plot. Now another thing that you can, a lot of plot character functions that lastly. So if you want to see what kind of functions are available, you can also, but you can also see if you plot a sequence, say 1 to 20, more than 20 options available. Let's say, for example, the first 20 options of vector function. So please do 20. So the options. By that, what I mean is, even instead of mentioning what kind of symbol you want, you can just mention the number corresponding to the symbol. So if I press the number 5, then what I get is these diamonds instead of that plus sign. And if I mention that I want the symbol on number 20th, then I get this. And so on and so forth. So there are other plots also available that you can see for diagnosis of the fitting that you have done, the diagnosis of residuals also. But I don't know how far we can go with them, but I'll just mention the functions that you can use for that, because theoretically we have not covered these things. So suppose instead of one plot, like in this window, we just created one particular plot. But instead of that, if you want some subplots, let's say 4 subplots in one plot window, what you can do is you can use this function called mfrow. So you'll specify, so you use this function var, var, and you'll pass the argument mfrow here. And this is basically a vector that will tell you that how many plots you want in a panel. So let's say it's a 2 cross 2 plot. So you want 4 plots in one frame. So it will divide your plotting region into a 2 cross 2 grid of panels. So this is how it will do it. You don't see it now because we have not plotted anything. So once you have created that grid, what you can do is you can plot whatever is available in the lm.fit, the fitting that we did. Okay, so it's giving an error that figure margins are too large. Basically the problem is just that the margins are too large, and you can specify the margins. Let's see if it is available in my history, how to do that. Yes, I did use that command earlier. So this is what it is. So I can just select any command from my history and tell R to put it in the console. And see, it puts it in the console, and once you press enter, it will run it for you. So I just check with these margins if it is possible to create that plot. And yes, it is. You can change the, so I've just randomly chosen the 0.5 option, but you can give different values and just check how you can fit the entire plot into the screen. It is not a really good plot. Okay, maybe I'll just check with the increased margins. See, I want to. So yeah, much better, right? At least you can see what is being plotted. So I'll not go into the details of these plots, but this is just to show you that you can get a number of plots. So a lot is going on when you're fitting a linear model. And this is one plot, let's say, I'll just discuss the first one. So you have residuals versus the fitted plot. And this basically will show you what kind of relationship is there in, with residuals and fitted values. Fitted values is the same size vector, so you can plot them together. Fitted is basically your y hat, y predicted values. And you can see that some kind of non-linearity is captured because this this plot should basically be a bit erratic. Like you should not be able to figure out any any pattern in this picture, but you can clearly see a pattern, a nonlinear pattern. Similarly, you can see it here also. So anyway, we'll figure it out what it is as we go further. It's a normal QQ plot between the two variables, and you also have, so what kind of distribution, it will basically show you how close it is to normal distribution. And then you have residuals versus leverage also. This is basically to detect outliers. Okay. So I'll just close this window. So I was just telling you that you can plot more diagnostics also. Once you have gone into further details of the linear regression fitting, you can do this. Okay. So one way was to fit them, plot them like this, which are the default plots that are available in this lm.fit function object actually. And the other way is you can directly plot also the predicted and the residual values if you just want the first plot. So what you'll do is you use the plot function. On the x-axis, you have the predicted values. So the predicted values are from this lm.fit. So that is the argument that you will pass. And then you have residuals also from the same object, so lm.fit. And you plot these two together so to get the first plot. Okay, so it's again plotting it in the same 2x2 structure. So what you can do is just mention that you want now a 1x1. Okay. And you get you can play around with the margins a little bit. Okay, I decreased them. So what I'll do is I'll increase them a bit. Yeah. Still not good enough because I don't see. Okay, we have not given the label name, so probably it will not show that. You can also specify what the y-axis and x-axis is by using xlab and ylab, the options that we used yesterday in the plot function. So again, play around with these functions to get better plots. Yeah. So at least now the axis is visible. And again, I wanted to plot this particular plot, the predicted values and the residual values, just to show you that there is some nonlinear relationship here, which should not be. Which basically means that something is there which is not being captured but can be captured by the model fitting. Okay. So now we have completed our section on the linear regression, the simple linear regression one. So since we have half an hour, so I think I'll be able to cover the multiple linear regression also. We can maybe have a 2-minute break, and if you have any doubt in this, or if you felt that I went faster with a few commands, so you can let me know and I can repeat those for you. Okay, assuming that there is no doubt here as of yet. So I'll just proceed further with the next section, which is on multiple linear regression. I'll just clear my console by pressing this Control plus L. Okay, one thing that I would like to tell you before starting the multiple linear regression module. I think yesterday I could not find the run command here. So actually what we missed was that you can find the run command just below the source. So if I can just decrease my console screen. Yeah, if you open, let's say this particular lab, which is actually what we are working on. So if you want to run a particular command, what I said was that you can select this command and press Control and Enter. But actually you need not select the command. And if your cursor is on the particular line, let's say line 8, and if you press Control Enter, it will run that command for you. And it will go to the next line. So you can again press Control Enter and get the next command. Similarly like this. So it will it will just ignore the comments and go to your next command and enter that, run that. Similarly, you can also, if you don't want to do the Control Enter thing, then you can just select it or not select it and use this run command. The current line or selection is here. So yeah. Okay, let's start with the multiple linear regression thing. I'll just bring my console back. Okay. So again, we can use the LM function that we used for the simple linear regression model fitting to fit the multiple linear regression model also. And the syntax for that is this. You use the LM function. You specify what your response variable is. And following the twiddle, you specify your variables that are the predictors, the independent variables. So in the case of simple linear regression model, we just had one predictor, so we had entered X. But now since we want more than one, so let's say we have 3 predictors, what we'll do is we'll type in X1, add the other variable X2, add another variable, let's say X3. So this is how you fit a multiple linear regression model, a 3 variable regression model to response Y. And then you can use again the summary function to summarize it. So we'll use the same data set, the median value Boston data set, and I'll just replace my response and predictor variables here with the variables present in that data set. So what you use is you use the LM function. Your response variable is median value of the houses. You use the twiddle to indicate that you are now going to type the predictors. And your first predictor, as was the case in the simple linear regression model, you use the LSTAT variable. So I'll use the same, I'm sorry, yeah, LSTAT variable. I'll add another variable, let's say I'll add the age. And I'll specify that the data is Boston. Okay, I just want to check if I don't type that the data is Boston, whether it works or not. Yes, it does work. So since we have used that attach argument, which has told R that these variables are available without telling them which where they are available, which data set they are from. So you can directly use this Y tilde X1, X2, X1 plus X2, because these are the 2 variables that you're using as predictors, and you need not specify the data. Just in case you have not specified and you have not used that attach option, you'll have to specify the data is equal to Boston or any data set that you are using. Okay, so now to summarize it, that what exactly this LM function has done. Okay, before using the summary function, what I'll have to do is I'll have to store this fitting into an object. Otherwise, R won't know that this has happened. So this has happened, it will print it, but it has not been stored in the environment. This lm.fit is actually from the last simple linear regression that we did. Right, so this is not what we want. We do the new fitting lm.fit. I'll just delete this one and create a new object with the same name, lm.fit. Sorry. And assign my linear model fitting, the multiple linear regression one, with the response variable median values and the predictors LSTAT. So once I assign this to an object, now I can summarize this object using the summary function. And you can see that as before, it summarizes it in a similar fashion. So you have the formula that this is what we have fitted. And these are the residuals. So this is how it is summarizing the residuals. And then you have the coefficients. So you have 3 coefficients here. The first one is your intercept. Then you have the parameter corresponding to the LSTAT variable, and then you have the unknown parameter corresponding to the age variable. Right, so you have 3 coefficients here and corresponding standard errors, t values and p values. And you can see that all are close to 0. So basically they are less than, the usual thumb of rule is again to reject the null hypothesis if your p-value is very small. And by very small, what I mean is you usually select a significance level. So p-value is usually compared to, let's say, 0.05. And if it is less than 0.05, you reject the null hypothesis. So So you basically keep all these three variables. From here, you can claim that there is a relationship between LSTAT and median value, as well as the variable age and the median value of the houses. Although these stars basically signify how significant the relationship is, because the p-value is really small. In this case, it is significant, but not as compared to LSTAT variable. Similarly, you have residual standard error, and you have R square, adjusted R square, F statistic, again far away from 1. So corresponding p-value, also see that. Now, suppose what I want is I want to fit the this multiple linear regression model, not to particular two variables, but to all the variables that are present in this Boston data set. So I have 12 predictors in this data set, and your one response variable is the median value. Except for that, the other variables present in the data set are your predictor variables. And what you would like to do is you want to perform this regression using all predictors. So instead of using this notation, the syntax that I told you, so if you use this syntax, you can use it, but the problem is that you'll have to then add each of the variables separately. Since you know that you want to fit all the variables, what you can do is use this syntax. So we'll store it again in lm.fit. And use the linear model function. So your response variable remains the same. You use the twiddle, and then instead of entering all the variable names of the predictors one by one, what you can do is just add this dot, full stop, which will basically tell R that you have to include all the variables that are there. And then you can just mention the data set, and you can even just leave it up. Just to check, you'll summarize this fit using the summary function. And you can see that R has used all the predictors that are there in the data set. So you can just check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yeah, you have 12 predictors. And corresponding to each predictor, you have the estimated value of the parameter. And you have the corresponding standard errors, t values, and p values. Now, looking at the p values, you can just see that whether that variable is significantly affecting y values, the median values, or not. So if you have a small p value, you can see that there are many variables with a strong p, with a very small p value, almost negligible p values. So they are significantly affecting the response variable, right? But here you also have two variables. One is age, and the other one is this variable, which I don't know what it stands for. We can just go back to the Boston data set and look what it's. So it's a proportion of non-retail business acres per town. So the relationship between this variable and our response variable, which is the median value of owner-occupied homes, is not really great. It could also mean that yeah, so it's not really great. That is what it means here. Yes. Right. Okay. So this is how you'll summarize your fitting of a multiple linear regression model, including all the variables. Now you can also like your summary basically gives you all these things, your residual standard errors and F statistic and R square. You can separately also access them if you just want the R square value, or just the residual standard error, or just the coefficients in this summary function. you can access them as follows. So what you'll do is you'll use the summary function, because we have not stored the summary anywhere. So we'll use again the same function, and followed by the $sign. You'll mention what you want. So suppose you want the R² value. So you can just press, okay, tab is not giving it. So maybe you'll have to enter R². And it will give you the R² value, which you can see that matches this value. So I think if you can save this in an object, let's say you are saving it as in an object called X. And then you can just check what are the things that are available in the summary. So you press the object name, you enter the object name, you enter the $sign, and you can just press tab then to know what are the things that are available in the summary sheet. So suppose you want the residuals, it will summarize the residuals for you. It will give you the entire residuals actually. So all the 506 values, right? And similarly, you can get R² also. So you can directly do it with the summary function, or you can store it in an object and access it like this. Like we access the variables of a data frame. Now, one more thing that you would like to know, and I think you will find it useful, is that particularly in the case where you have too many variables, and you don't want to choose 2, 3, but you know what you want to exclude. Since we summarized this last regression, this multiple linear regression with all the fitting. Okay, I'll just clear this window, and what I'll do is I'll repeat my command where we were summarizing this fit. Yes. So this is the fitting of the multiple linear regression model with all the variables in the Boston data. And we can see that these two variables, let's say, this age variable and this indus variable, they both do not seem to be affecting the output variable as much because they have a high p-value. So we may want to just run the regression, the multiple linear regression model, excluding these predictors. So let's just say I want to exclude the age predictor. So what I'll do is I'll use, I'll fit again, but let's say I'll fit in in an object called lm.fit1. I'll use the lm function, and to the response variable with the twiddle function, I'll just specify the predictor. So I don't want to specify each and every predictor, so I use dot. But now I want to exclude one of the predictors, which is age. So what I'll do is I'll use this age with a minus sign, like we do for the indexing also, if you remember from the last session. Right? So basically it's the same command, just that you are excluding the age variable because it has a very high p-value. So now you want to perform regression without it. So you exclude it by subtracting it. So now if you summarize, lm.fit1, this is what you get. So the age variable is not there. So the same thing, this updating thing, like you are updating from 12 variables to 11 predictors. So you can also do it using this update function. So what I'll do is I'll go to this previous command. Yes. So what I did with the previous command was that I did a new fitting. lm.fit1 is the object where I saved this new fitting, and I fitted this Y response with all the predictors and excluding this age one. So now what I can do is instead of passing this command again, I'll just select this and update it as follows. So I'll use an update function. And in the previous fitting, we used the all predictors. So I'll use that fitting lm.fit, where we have used all the 12 predictors to predict median value. And I'll mention in that update function that I want to delete this one variable, h. So it's the same syntax as we use for the fitting. Twiddle followed by this dot. Dot is to represent that we want all the variables except this age variable. And it will give you the same results. You can just check. You don't have the age variable here, or neither do you have it here. You can similarly remove this in this function also. I'm sorry, in this variable also, not the function. And do the regression without it. Okay, another thing that I would like to cover is that you are fitting a multiple linear regression model, but now you're also including the interaction terms. So suppose your x1, x2, xc, the predictors also have certain interactions and you want to take that into consideration. So you use the same function lm, but now there's a different syntax for including the interaction. So what you can do is you use this lm function. And suppose what you want is you want to, your response variable obviously remains the same, but the predictors, let's say if you want the LSTAT predictor and let's say the other predictor that you want is age. So if you want just those two predictors, then the usual syntax is this LSTAT plus age, right? This is what we discussed. But now what I want is also an interaction between LSTAT and age. So what I'll do is I'll just replace this plus sign with this asterisk sign, which basically tells R that I want LSTAT as a predictor, I want age as a predictor, and I want the interaction between LSTAT and age also. So it's a shorthand for, I'll just write that as a comment here. So it is a shorthand for LSTAT and age and LSTAT interaction between LSTAT and age. So this is what the interaction, this is how the interaction term is included. So just in case you don't want the age, but you do want the interaction between LSTAT and age, so you can just remove this age variable and you can mention that you want the LSTAT and you want this interaction. In case you want all the three, the variables and their interactions, then you use the multiplication function. Okay, I hope that's clear. So this is what we are doing. We are now fitting the linear model, the multiple linear regression model with this LSTAT and age and their interaction. And I don't think we need to specify the data set, so I'll just skip that for this command and I'll summarize using the summary function and see what it looks like. So see. So now you have again 3 variables. I'm sorry, so you have coefficients corresponding to 4. So you have, yes, the first is the intercept, so that is not corresponding to any variable. So yes, 3 variables is not incorrect. So then you have the LSTAT variable, the predictor, you have H predictor, and you have the interaction between LSTAT and H. And you have the corresponding estimated values. You have standard errors, you have t values, and you have the p values. And you can again see that this intercept term is significant. The LSTAT is again has a small p value, so this is good. And H is has even a higher p value than before. So H is not a very significant variable, which we can exclude. And then you have interaction between LSTAT and H, which is less than 0.05, so you can accept this, right? Okay. So this is how you include the interaction terms while fitting the linear model. Another thing that can come handy is you want to probably use the nonlinear transformations. So if you remember that I focused on this when plotting the linear fit before, and I showed that the residual and versus the fitted plot was showing some nonlinear pattern. So which basically sometimes indicate that if you use the nonlinear transformation of the predictors, then probably you'll get a better fit. So for instance, if you want to create a predictor x square, what you do is you use this syntax for that. So I of, let's say your x is a predictor, but now you want to include x square term also. So this is how you do it. So this I is basically to wrap it. So what it means is it has a, because if you use just x square, what it will do is it will just square the elements of x. So x square has a separate function, right? This raised to the power function will tell R to just square the x. So in order to not do that, what you do is you use this I. So this is basically this, it is needed since this raised to the power is a separate has a separate meaning altogether. So since when we fitted the simple linear regression model between LSTAT and median value, what we saw was that there is a okay, I got a notification that the MCQs are about to start. So I'll just finish this nonlinear transformation one. I'll just show you how to include that. And we'll finish the session by concluding from here. So if you want to fit a nonlinear fit, so you want to fit LSTAT and LSTAT square. That is your predictor that you are fitting using to explain median values. So what you'll do is, let's say you are storing this into lm.fit2 using the lm function. Your response variable, your twiddle, and then you specify that the first predictor is LSTAT and the next predictor that you want to use. So you add the next predictor and the next predictor is LSTAT square wrapped around this I function. And you can summarize this. And you can see that how the p-values corresponding to both LSTAT and LSTAT square are actually very small, in fact negligible. So both are significantly affecting your response variable. And therefore it was a good idea to include this x square, LSTAT square. So there were a number of things like ANOVA and polynomial fitting and things like that, which I wanted to cover. I wanted to cover qualitative predictors also, but I don't think that the time will allow us that. But in case you have any queries on what we have covered and what we can do more, you can always write to me. My email ID, you can find it on IIT Guwahati on Mehta Family School website also. And I think I'll provide you all the details. So this. So there are no Hello.
Thank you, madam.
Yes. Okay, I can leave. The MCQ has started already.
Ma'am, we will just make the link active. Thereafter, participants can give the answer.
Okay, perfect. So I'll take your leave. Thank you. Thank you for the invitation. And I hope things were clear in this session and before. And I would request all the participants that in case of any doubts, you can email E&ICT or directly to me also. Okay, thank you.
Thank you, madam. Dear participants, the MCQ link is active. We have shared the same link in the chat box also. You please try to solve the MCQ. It includes only 15 questions. Each question is of 2 marks. There is no negative marks. Please try to complete it by 5 p.m.
देखिए इसको
Linear regression is a standardized learning algorithm. True or false?
हम लोग को लॉकडाउन की वजह से क्लियर नहीं क्योंकि लॉकडाउन की वजह से हम लोग को नहीं बनना होगा
இடமே கிடைக்க மாட்டேங்குதா? எங்கடா லீவுடா எங்களுக்கு? லீவா? சரி எத்து லீவ் எங்களுக்கு இன்னைக்கு தான் காலேஜ். நான்லாம் இவனு நானும் மேலே உட்காந்துட்டு தான் வரணும். யார் வருவா? ஜெகதீஷும் இல்லையா? யாரு போட்டான்?
Yes, is there any query? Yes, sir, please tell.
So the quiz isn't. So the quiz don't give the negative marking, right?
It is having score of 30 marks.
எப்படி எழுதுறீங்க? 5 ரெக்கார்டு எழுதணும், 2 ஜெராக்ஸ் போட்டோம். அப்சர்வேஷன் கூட 2 லாபம் ஒட்டுக்க செய்யணும். சின்ன பஸ் வரும்போது மேக்ஸிமம் எனக்கு இடம் எப்பயாச்சு எப்பயுமே இடம் கிடைச்சிருக்கேன். எப்பயாச்சும் ஒரு டைம் உங்க பிளேஸ் ஃப்ரீயா இருக்கும்.
Participants who have submitted their quizzes, they can leave.